So welcome to Automated Automata with James Dalessandro. As you know, I'm sure by signing up for this webinar, I hope that you know, it's a Grasshopper C# webinar with heavy focus on C#, mostly C#, and looking at cellular automata is as the main kind of algorithm that will be used to designing. Requires obviously Rhinoceros and Grasshopper, and then plugins, I think Dendro and Pufferfish, but they're not the main focus of this webinar.
And they're not even that necessary, really. They're just for like a little, if you don't have those, it's actually not going to be a problem. That's mostly for just like visualizing or something.
Yeah. So I'll introduce James. So James is a Boston-based computational designer and artist. He's co-founder and director at Emergent Design and design technology company focused on delivering computational solutions for complex design goals in the field of architecture, design, and engineering. Inspired by the combination of mathematics and beauty of natural phenomena, James' work explores applications of generative form, rule-based systems, graph theory, and traditional computational geometry algorithms to draw a bridge between formal product design and current digital design paradigms. So welcome, James. I'm going to hand it over to you now. I'll be here the whole time in the background. And yeah, everyone, please enjoy the webinar.
Thanks, Mike. Hey, everybody. How you doing? I got 3 monitors, so I'm going to keep the chat and stuff over in my monitor that you guys can't see. So if there's any issues, like I forget to zoom in on the script editor and you guys can't read what I'm writing, something like that, somebody just say something in the chat and I'll be able to see that sort of thing. I do have kind of like a little cough right now too, so I'm going to try my best to mute myself every time I cough so you guys don't get your eardrums blown out if you're wearing headphones. I'm going to share my screen now. Oh, who's disabled participant screen sharing?
Well, maybe should be good now.
Okay, yeah, cool. Screen 1, share. Okay. What's up, guys? Do you see which screen do you guys see?
See Rhino and Grasshopper.
On the left and right screen? Like left and right side or up vertically split?
From my end, Grasshopper is on the left.
Okay.
And right.
Yeah, perfect. That's what I need. All right, just gotta put my chat window up. I get the QA window open too. Nice. Now I've got that all in my upper right area. Okay, guys. Let me move this. All right. Guys, welcome to Automated Automata. Automata, I'm not sure how that word is really pronounced. I say it both ways sometimes. Yeah, like Mike was saying, this is going to be really heavy C#, so I hope everyone is semi-comfortable with it. It's not going to be very advanced C#. So if you just have like a pretty basic understanding of C#, if you've coded a few things, you'll probably be able to follow along, no problem. There may be a few things that you've not seen before, but I don't use any like very advanced coding techniques in this webinar. So first things first, I'm not sure how much you guys know about cellular automata at all, but so let me just introduce it. If you give a quick Google to cellular automata and check out Google Images, you see a lot of these triangular looking things. This is a result of one-dimensional cellular automata. Or you might see something like this. This is an example of two-dimensional cellular automata. Or you might see something like these, which is on the left side of this picture. I would call that 2.5D cellular automata. And on the right side of that, it looks like, to me, three-dimensional cellular automata. And we're going to be going over all of those. 1D, 2D, 2.5D, 3D, and if we have time, which I think we will, we'll also be able to do a little bonus. I've got a cyclic cellular automata, which is a little different, and that's also going to be in 2D, but that is a pretty cool one. So that's like a little bonus if we have time, but I think we will. So probably the most famous cellular automata that you guys may have heard of before is called Game of Life. Oops. If you just search Game of Life, though, you get the board game, so you got to say Conway's Game of Life, because John Conway is the mathematician who invented this, or yeah, he's the mathematician who invented this. So if you see this GIF here, that's like a pretty good representation of what Conway's Game of Life looks like. You have this two-dimensional grid, so you can think of it as like pixels, right? And they're either off or on. So in this case, the white is off and the black cells are on. And so you have this two-dimensional grid of cells, and each one of those cells looks at the cells around it to determine its state in the next frame or the next iteration, basically. And you can see in this image here, we've got some different known formations that occur in John Conway's Game of Life. And oh, here we go. Here's a good picture here. This kind of shows how you have your current generation, and then the next generation, it changes based on the cells surrounding it. So you can have different rules that decide how the cells change according to their neighbors, but the basis of all cellular automata is essentially that you have cells in some type of grid, and they examine their neighbors, and then they change their state based on that. So that might be over time, or it might be through space in the case of one-dimensional cellular automata. So you might have heard of John Conway's Game of Life and seen like something like this. It's such a small image, but seeing something like this where you've got these little guys gliding across the screen. We actually call these guys gliders. Oh, I don't know. Can you guys see my mouse? I hope you can. It's not really that big a deal, but okay, great. Yeah, so you see these guys, and they're coming out of this weird formation at the top there. Those are called gliders, and it's a cool formation that happens, and they move across the screen diagonally. And so at the top here, this formation, we'd call this maybe a glider gun, because it is a stable formation that just continuously spits out gliders. So there's lots of different formations that are known in John Conway's Game of Life, just because that is the most studied one. So there's like lots of names for all these different little formations you have. Like here we have the toad, beacon, pulsar, glider, lightweight spaceship, beehive, boat, tub, etc. So they're like named little formations because they do different things and they're so commonly found. But that's really just because Conway's Game of Life is the most common or the most popular, most studied one. But that's a 2D cellular automata. So you might have actually heard of Stephen Wolfram or Wolfram Alpha, which is like a website, but he writes a lot about one-dimensional cellular automata. And you might be looking at an image like this and thinking, how is this one-dimensional? Clearly it's two-dimensional. But essentially, one-dimensional cellular automata, you look at each row, just this first row, and then you move to the next row, and that's the next iteration. So really, the one dimension is just it's a singular row instead of the full 2D grid like you look at in 2D cellular automata. So you can think of one-dimensional cellular automata as like the rows are over time moving downwards in the image. So first you have this single cell in the middle, then you have 3 cells, then you have 2 and 2 gap, and then 1, and etc. It goes from there over time downwards. And we call this type of cellular automata either one-dimensional cellular automata or elementary cellular automata. And you can get some really cool formations from this, or patterns and things, and a lot of them can become really chaotic or unpredictable, which is very cool. And they even use some of these in like cryptography to generate like codes and things like that, because some of them are so chaotic and unpredictable that you can't really like simulate them in a way that you could, like, I don't know, it's good for making like passwords or something like that. You'll see that some of these say like rule 57, rule 62, they're named rules. That's because elementary automata, and we'll find, has 256 different rules. And I'll explain why that is and how that works, and we'll code that. But there's only 256, so they're enumerated. So you can look up I know on, oh yeah, this is a link to Wolfram right here. So if there's like on Wolfram, they have like an encyclopedia of the elementary cellular automata. And you can look at every rule if you want. Like here is every single rule. So that's on wolfram.com. If you just search Wolfram elementary automata, you'll be able to find this page. So this is every single rule that exists in the elementary automata. But there's quite a lot of them that are just inverse rules. So like this is like black on white, but then down here we might have the same rule, but it's white on black. So even though there's 256 rules, there's actually quite a few that are just mirror images or inverses of another, or rules that don't really do anything of interest. Like they make a single line or just a single cell and then it dies out, or it fills the screen with black. So there's a lot of rules that are really not that interesting, but plenty of them, especially rule 30. Rule 30 is extremely interesting, and it's one of the ones that they use for cryptography. Rule 30. It even has its own Wikipedia page, and you can see it on things like in nature, similar patterns form on like seashells and stuff like that. So Rule 30 is a really cool one, and we'll definitely be able to see that as we go. But it's one of the most interesting ones because it's so chaotic and unpredictable. There's quite a lot of them that sort of form repeating patterns, and that's like not that interesting. But this one always generates like new and interesting rows. You know, it never it's not periodic. It doesn't cycle back to the same pattern over time. So that's really cool. So there's, well, I guess I'll show you a little bit of 3D. So people call this type of thing that I'm going to click on here. People call this type of thing 3D cellular automata, or this type of thing 3D cellular automata, or like this is a good one. But really, this is what I would call 2.5D cellular automata, because actually it is just the 2D cellular automata, and then they stack these layers in the Z direction over time. So you have every iteration stacked in the Z direction over time. So that is similar to how one-dimensional cellular automata is just one row, but then we move it down the page and create a 2D grid. This is a 2.5D cellular automata because it's not actually considering the cells surrounding it in 3D, just in 2D, and then we move that over time. So there's a lot of Grasshopper tutorials that are like, oh, how to make 3D cellular automata in Grasshopper, but actually it's just 2.5D cellular automata. And I'm going to set the record straight today. We're going to do some real, true 3D cellular automata today. Okay, so enough background. Let's go to Rhino. All right, first I have a little explainer here for how 1D cellular automata works. Load that up. Okay, there we go. Let me just change this to be solid color. Okay, great. All right, so like I said, and I could probably move this over so you can get a bigger view of this. Like I said, one-dimensional cellular automata is concerning just a single row. So we can call this a grid, but it is a like 1 high by X long grid. So this is a one-dimensional grid, which is really just like a row, right? And in all the cellular automatas that we're going to look at today, we're just going to be concerned with 2 states, whether the cell is off or on. So in this case, we have a one-dimensional grid here, just a row, and there's 7 cells, and all of them are off except for the middle cell, which is on. So this is basically like you could have this be the starting condition of your elementary automata. We have 3 cells that are off, 1 cell that's on, and then 3 more cells that are off. And in one-dimensional cellular automata, the classic one, what we're concerned with is we're going to call this a neighborhood. And that is, if you're looking at this cell, the neighborhood of this cell is this one, and this one. So it is itself and the cell to the left, and the cell to the right. So if I was looking at this cell, the neighborhood would be this cell, and this cell, right? So for this cell on the left here, we're going to wrap around. This is its leftmost neighbor, okay? So for this first cell here, since there's no cell to the left of it, what we're going to be doing in all the coding that we do is consider that this cell is its left neighbor. So for this cell, its neighborhood will be this itself, its left neighbor, and its right neighbor, okay? And then this cell will be, the neighborhood is these three cells, this cell's neighborhood is these three cells, this cell's neighborhood is these three cells, etc. And when we get over here, it's its left neighbor, and this is its right neighbor. So just so we get that straight. But basically, we're going to be calling this the cell's neighborhood, okay? And we're concerned about the configuration of that neighborhood. So right now, if we're looking at this center cell, the one that's on, its neighborhood is 0, 1, 0, right? And how many ways can you actually organize that? Well, it turns out there's only 8 ways. That can either be 0, 0, 0, 0, 0, 1, 0, 1, 0, all the way up to 1, 1, 1, right? So those are the only ways this could possibly be arranged. There's no other way that you can have 3 cells with 2 states arranged in any more ways than these 8. So that's really important because we have 2 cells and a size 3 neighborhood, 2 states and a size 3 neighborhood. That is 2 to the power of 3, and that equals 8. So it turns out you can mathematically figure out how many different neighbor configurations you could possibly have for a given cellular automata based on the states and neighborhood size. Because you can have cellular automatas with more than 2 states, but today we're going to be just talking about on or off, 1 or 0 or 1, just a 2-state cellular automata. So if you're looking at this neighborhood and you see 0, 1, 0, right, that is right here. That's one of the possible 8 states. And what you can do is apply a rule to this where you look at each neighborhood and you say, okay, if it's 0, 1, 0, I want that next cell, when it comes down into the next generation, 0, 1, 0 means that cell becomes a 1. But if it was 0, 0, 1, right, this one is a 0 currently, and its neighborhood is this one, and this one, we find that this rule turns it into a 1. So in the next generation, this cell will actually be a 1. So in this way, we move over time, and we'll look at each cell in the row, and then make the next row based on that, based on the rule and its neighbors. So this is how this works, right? And looking at this number that we have here, we call this the rule. This is a binary number, 0, 1, 1, 1, 1, 0, 0, 0. That actually comes out to be 120. And as I said before, there's only 256 rules. So this is rule 120. And in fact, all these are also binary, obviously. So it goes from 0 to 7, right, in binary. So if we're going to use rule 120, which is just a random arbitrary rule that I decided when I was making this example, and we're going to use this as the initial starting condition, how will this move forward, right? So this is 0, 0, 0, 1, 0, 0, 0, just like up here. So this is that first row. And how will it react to that second row? How will we create that second row using rule 120, okay? Well, we look at each of these cells, like this one, and its neighbors are this one, itself, and this one. So that's 0, 0, 0. So the next cell is also going to be 0. Okay, no problem. Then we look at this cell. Its neighbors are the same. Its next generation is going to be 0. But then we come to this cell, and its neighborhood is 0, 0, 1, right? And we know that that means that the next cell is going to be on. And look at that, it is. And we can go over each one, but I'm just going to skip because it's kind of boring to explain it by, by just like talking about it. So I'll show you what the next generation will look like, and the next generation will look like. And this is just following the simple rule of, based on the neighbor configuration, we either turn the cell on or off in the next generation. And then interestingly enough, this comes out to be a single cell again. So following that same rule, we know that this is going to be a cyclic pattern that this forms. This will just continue to do this same formation over and over and over again. But that's probably just because I only have 7 and it was a symmetrical starting condition. So if I started with 2 cells on somewhere, we might get something chaotic and not periodic like that, which can be really interesting. So if we have 0 or 1, that's 2 states, right? It can either be on or off, or sorry, 0 is off and 1 is on. So I'll say it can either be off or on. That's 2 states. We have a neighborhood size of 3, right? We're concerned with the current cell, its left neighbor, and its right neighbor. That's a neighborhood size of 3. So 2 to the power of 3 equals 8 possible neighbor configurations, which we've already figured out here. There's only 8 ways you can arrange these neighbors. And that comes out to be 2 to the power of 8 is 256 rules. And we've already found that this is rule 120 out of 256. So you have rules 0 to 255 is your possible number of rules. And you're probably thinking, well, that's not that many rules. So like you could easily go through and look at every single one of those. And then, maybe you get bored of those rules because that's just not too many. There's not a lot of variety. And you want to see some more complex patterns and things like that. Well, good news is that there is a way to easily extend this to a massive number of possible rules. And all you have to do is, instead of having a neighborhood size of 3, if you have a neighborhood size of 5, and you look at one more cell to the left and right of each cell, so the neighborhood size now would be like this, and this is the cell we're talking about, and its neighborhood is now 5 cells wide. That actually means you have 32 possible neighbor configurations. So there's now 32 ways you can arrange those neighbors. And that comes out to 4,294,967,296 different rules. So quite a bit more than the 256 rules. So we're going to code first the regular elementary automata, 2 states and 3 neighbors. But then we will modify that code to be 2 states and 5 neighbors. And then you will have so many rules that you will never possibly see all of them because it's just a huge, huge number. So that's really cool. And also, because it has 5 neighbors instead of 3, you also get like more complex patterns because different things can happen when you have to consider that many more neighbors. So that is the basics of one-dimensional cellular automata. And we are going to dive in now. Is there any questions on that before I get started? Anything you're not 100% on or anything like that? Let me know now. So just open a new Rhino blank thing. Split my window here so I can show you Grasshopper and Rhino at the same time. If no one has any questions on that, we're going to jump right in then. That's good. So we know that you need to have those rules. You know what? I shouldn't have gotten out of this page. Hang on. This might be confusing to explain without the visual. Let me show this again. Okay. All right. So we know we have 256 rules, right? So we want to be able to explore all of those rules. So I'm going to make a slider from 0 to 255. And I'm going to call this rule, because this will be, where we choose what rule we want to visualize in the end. But the actual code is going to want to see it in a binary pattern like this, 0, 1, 1, 1, 1, 0, 0, 0, instead of 120 or whatever. And I'll put this on 120. So we'll be using rule 120. I have whatever this is called, bifocals active. So when I put any component down, you'll be able to see it. But the unfortunate thing is that bifocals doesn't tell you the range of sliders, and 90% of the actual Grasshopper components we're going to be using today is just sliders. Mostly C# and then just sliders. There's going to be some components though. So this is a slider from 0 to 255. Okay, so that way we have 256 rules. But like I was saying, instead of having this number be 120, we want to change it into this binary representation. So we're going to make a little helper code to decompose this number into binary. before we bring it into the main code. So we're going to make a C# component. And I guess I'll briefly go over the anatomy of this C# component, C# script component, just in case this is really someone's first time, but I really hope it's not. So we're not going to spend a lot of time on this. So you have the C# component, you have the output, which is basically like this little balloon here that shows you the warnings and errors. You have an A output, and you have an X and Y input by default. And you can obviously add and subtract your inputs and outputs by zooming in. Just for a quick refresher for anyone, here's how this works. You can right-click on the input and rename it to things. Like I'm going to name this to test, so we can follow along and make this component with me. It's going to take 3 minutes. We'll call this test. Then you right-click. You can see you have item access, list access, and tree access. If you used Grasshopper before, you know that certain components expect you to send in a single item, or expect you to send in an entire list, or they expect you to send in a tree. So something like shift list, right? This component, shift list, isn't going to work if you put in just one item. I mean, it's not going to do anything. So that requires you to send in a list. So we are going to need to pay attention to what the input is expecting. But here, we can leave this at item access. So that means it's expecting one input. Then if you go to type hint, you can see all these different types we have. And this is also important because, as you know, if you put in something that can't convert to another thing, like if you put in something to, I don't know, the line SDL component, right? And you put in like a number into the direction input, it's expecting a vector. So that's not going to work, right? The start is expecting a point. It says empty point parameter, right? This says empty. Well, not empty. This is expecting a number. So different inputs expect different types of data, okay? And since we're making our own components, we need to specify what type of data is supposed to come in. So for this one, you can click bool, which is Boolean, and I'm going to put a toggle, a Boolean toggle. And then I'm going to stick a panel coming out of this component, just so I can see what we get from it. And then I'm going to double click the component. I know I did that a little fast. I'm going to double click the component, and out comes this window. This is like what is inside this C# script component. So in here, I'm going to say if test. Okay, so here actually, I need you guys to tell me, can you read this or should I zoom in? Because I can make the font bigger for you guys. But somebody let me know if you can. Let me see what the default size is. I think this size. Can you read this? A bit smaller, readable. All right. It's annoying because it doesn't hold the zoom in size, so I'm gonna have to remember to zoom in every time. Is this size okay? I don't want to zoom in too much because a bit bigger, even bigger than this. All right. All right. We're gonna be scrolling sideways a lot if I zoom in too far. Honestly, though, I can stretch the window, I guess. So, okay, this is probably okay. All right, so we're inside this component here. I'm going to write if test, and that's the same as saying if test equals true. So we're testing this Boolean value. So if test, and some brackets or whatever these are called, curly braces. Then I'll say A equals, and some quotes, and I'll say hello world. And that is the full code of this test component here. So you can see when it's false, nothing shows up in the panel. But when I turn it on, hello world comes out. So we're putting in a Boolean. We're checking the value of that Boolean, whether it's true or false. And if it's true, we're going to output hello world. Very simple component. That's really the basics of C# script component. And if we wanted, we could have, like, you know, if test is not false, have an output come out of B, which is a new output I just added to this component. So those are the basics, but I hope that isn't new to anyone, because if it is, you're probably going to have a pretty hard time following along. Okay, so let me grab my script for my other monitor. All right, we're going to drop down a new C# component because that other one was just a test. I'm going to get rid of the Y input because I only need the one input here. Let me actually, I don't need as much Rhino as I need Grasshopper. Shrink this a little bit. Cool. Nice. Okay, so now I have a little bit more room in my Grasshopper window. We're going to right-click the X input. We're going to change that to say rule, because that's what we're trying to take in. We're going to take the rule and put it in there. But we also need to make sure we set this to int, because this is an integer we are putting into this. So now it is expecting an integer. We're going to plug that in, and we're going to dive into this component. So remember, in this component, what we're doing is changing the number from 120 into a binary representation of that number. And this is just a little helper component that I'm going to call the 3-neighbor rule set generator. So, oh yeah, I got to zoom in. Can't forget. What I'm going to type in is component dot message and then quotes, and I'll say like 3n rule set generator, and then semicolon, and I'll hit OK. And you can see how that comes out now here on the bottom. So I like to name my components like this. And you notice I call this the rule set generator, right? If this is the rule, 120, this number, then the rule set is this binary, 0, 1, 1, 1, 1, 0, 0, 0. That's the rule set. That's what I call it. I'm not sure if there's a proper name for this, but I call this the rule, and I call that the rule set. So this is the rule set generator. It's going to take in the rule and output the rule set as a list. But first, zoom in. Can't forget. First, we're going to get the binary representation of the rule number. So just label what we're about to do. Get the binary representation of the rule. And in C#, it's actually pretty easy to do this. We're going to get it as a string, which is like what we have in quotes here. So even though there's a number in this string, it treats it as like a sentence, right? A string, pretty common data type. So I hope you know what that is already. We're going to call it string binary equals, and we're going to say convert with a capital C dot toString. And the input, what is it asking us for? It's asking us for an object value, or here we go, int 32 value. That's exactly what we have. We have an int coming in. So I'm going to say rule, and we are going to provide it with a format provider. And this is basically like we're converting it to a string, but how do you want to convert this number to this string? I want to convert it as binary, and it turns out the 2 is like the index for converting it to binary. This is just like a built-in C# thing. So don't worry what that 2 means. That's just like how they decided to do it. All right, so we've got string binary equals convert.toString rule 2. So that basically line means we're getting the binary representation of the rule number. But let's check that. Okay, so I'm going to say A equals binary. And I'm going to hit OK. And I should pop a panel on this so I can check my result. And look at that. When I now scroll this list, or scroll this slider, you can see it going from 0 all the way up to 8 ones, which is perfect. That's exactly what we need. So that's why I stopped at 255. If you go to 256, we'll get another digit, and it'll be like 0, 1, 1, 1, 1, 1, 1, or whatever it is. So this is perfect. This is what we need. Jumping back in, because we actually need it to be, here's one issue we're having right now. It's nice that there's 8 digits when it's fully filled up, but when I scroll back to lower numbers, there's only 5 digits here, and 0 is just 1 0. But I always want it to be 8 digits, right? So what I want to do is pad it with, prepend it with zeros if it's less than 8 digits. Like this 11011 should be 001111 or whatever. There should be 8 digits, and we should fill it in with zeros if it isn't 8 digits. So how we're going to do that is actually quite easy. We're just going to add on to the rest of this first line here, dot pad left 8, and the character we're going to use a single. This is basically saying pad it to the left, this number, with 8 digits always. So there's always 8 digits, and then add a comma, and then add a single quotation mark or whatever that's called, 0, and then your thing there, your ending. So what this is going to do now, when I scroll around here, it's always 8 digits, and 0 is now 8 zeros, and then 1, is 0, 0, 7 zeros, and then a 1, right? So it's always 8 digits. So that's exactly what we need. I'm sorry that every time, when I zoom in, I hate that this little thing shows up, so I can't like zoom in that far for you guys. Oh, you know what? I can increase the font size. Is that good? So you can see that there's always 8 digits now. And if there's not 8 digits, it will prepend it with zeros. So that's perfect. That's what we need. But I don't want it to be a single, or this is a separate line? No. Not a separate line. It's just at the end of the thing there. Just like this. Okay, but I don't want it to be a single string like that. I want it to be a list. I want to output it as a list of numbers. And in C#, this is going to be maybe a little confusing, but we'll just all have to work through it. There's arrays and lists, but in Grasshopper, there's just lists. So I'm going to call it outputting a list, but really we're going to be creating an array. Basically in C#, an array is something you know the total amount of. Like I know there's going to be 8 numbers in this array, but a list is something you don't know how many things you're going to add to it. Like if I didn't know there was going to be 8, if it could be 7 or 9 sometimes, I would probably make a list instead. But for right now, we're going to create an integer array. And the way you do that is int, and then square brackets. I'm going to call it rule set, because this is what we're going to be outputting, right? And that's going to equal a new integer array of size 8. So this is how you create an array. So this is basically an empty list of numbers right now. It's an empty list, but it's expecting integer type, right? I said it's an empty list of numbers. That maybe sounds strange, but it's an empty array waiting to be filled with numbers. So it's expecting numbers. And if I were to put it by saying a equals rule set, it's all zeros. So that's what happens when you create an array of ints. It fills it with zeros, I guess. I actually didn't know that. That's good though. So back in. All right. So now what we need to do is take this binary, the string, right, and take each character and then add it as a number to this list. So we're going to convert each character in the string to an int and add it to the array we just made, right? And that's what we're going to do in this step. So we're going to use a loop for this. So for int I equals 0, I is less than 8. We know that it's 8. There's only 8 numbers. I plus plus. So set up your for loop. And in this, we're going to make a temporary integer just by saying int temp. Then we're going to need to convert each number in this string to a number, which is kind of an annoying step, but this is the easiest way to do this, I think. So how I usually do it. So what we need to do is try to convert each character in that string to a number. So what we're going to do is type int dot try parse. So we're trying to parse each character as a integer. That's essentially what we're doing here. That's what this thing does. But instead of expecting a single character, if you see when you open the parentheses, the suggested things for this function is a string s. So annoyingly, we're going to now say binary I, and what this means is for each character, right, in the string, binary I dot toString. So convert each character to its own little string, and then we're going to say out temp. So this is going to pass each of these as an integer into this variable we just created. And then now I can say rule set I equals and assign the ith index to this temporary variable now. And then when I have a equals rule set, you'll see now we have all of these coming out in a separate list, right? So now we have each of them from 0 to 7 indexes in a little list here. So that's exactly what we want. And that is the complete 3-neighbor rule set generator. Pretty easy code, nothing crazy. Here it is, really big, so everyone can see it. If you're watching the recording, pause it here if that's what you want. So that is what we're going to use. This is our little helper script that we're going to use to generate the rules when we make our actual main thing here. So I will now copy this just move it down. I'm just going to be like copying and moving things down so that I don't like overwrite each step, just in case we need to go back or something like that. All right, so first things first now, we've got our rule, but we want to create that first row, right? Just like how this is, you have to start off somewhere. And since that doesn't follow any rule, it can be random. So we're going to need to create another C# component. And the inputs to this, we are going to keep X and Y, but we're actually going to capitalize those. Capital X, capital Y. Make sure you change those to ints, the type hint to int. And we're going to add another input. We're going to call that seed. We're going to make sure that's an int as well. And then we're going to make another input, and we're going to call this rule set. So, right, we took the rule, we output it as the rule set, and then that's going to get input into here. But make sure on rule set, you change this to list access, because we want to consider the entire list at once. We want to look at everything in the list, not each item individually, but list access, because we're passing a list into this input. So make sure you set rule set to list access, and the type int should also be integer. Then we're going to add another input. We're going to call that chance. This will be a item access, and it will be a double type. A double is like a decimal number. So we're going to make a slider from 0 to 1. And whenever I make sliders, I usually do the like dot dot type of thing, because that means you can create it with a range already. But I know you can do like the less than sign or something like that and also make it that way, but that's just not how I do it. So anyways, all you need is a slider from 0 to 1 with some decimals, because we don't want to just be 0 or 1. We want to be able to pick in between. So I don't know, I put 4 decimals. So we'll call this chance, plug that into the chance one. For the seed, I always just like make a big number, so there's at least like 10,000 different possibilities for the seed. I will call that seed. Move this up maybe so I can see better. We've got X, Y. So these are going to be the size of our grid here. So in this example here on the right, we've got X is 7, and then Y is, I don't know, whatever, like 9 or something. Obviously, that's not very big, so we want to have a bit larger. So I'm going to make some sliders from 0 to 100, and those are integers, of course. I'll call this one X, copy paste it, call that one Y. And I'll just make sure they're not the same number, just so I know that things are working the right way. Okay, one thing you can check, one way to check that you have everything all set up right, is double-clicking on your C# script and looking up here at the inputs. So make sure it should say int X, int Y, int seed, list int rule set, and double chance. So if it says like object or system.object X, that means you didn't right-click and set the type hint. So it's important to set that what it is expecting to get correctly. I'm going to back out and make sure I attach my panel just so I can see what we're doing when we expand. Pretty soon we'll be getting some cool visuals in Rhino, but for now we're still working with just little panels. But that's no problem. Okay, get my code up in the left window here. All we're going to do here is just initialize that first row. So this is just initializing that first row. Let me zoom way in. Okay, so this is going to be a component for initializing the first row of our one-dimensional cellular template, or 1DC. Okay, so first things first, we need to create a new random with the seed. So we do that by saying random rand. You can call it whatever you want. No, you cannot edit the text in the gray areas. You call it random rand and say equals new random, and in parentheses we're going to put in our seed. So this just means that when we change our seed, our random generation will also change, and this allows us to quickly get new variations of things. Create a new random, perfect. And then we know that what we're going to have as the output of this is a grid. Even though right now we're just worrying about that first row, we are going to have a grid in the end. So our output, we're already thinking about what our output is going to be. It's going to be a data tree because it's like, you know, a two-dimensional. It's list of lists. So, you know, you have a list of rows, and each of those rows holds so many cells. So it's a list of lists. So we're going to use a data tree for that. So we're going to say int data tree for eventual output. I just like to put it up first because then I know what I'm adding my data to as I go, and then I output at the end. So I'll call this data tree of a type int, call it output. That is a new data tree. Int, int. If you just got that same issue that I just did, where it changes it to say interpolator, you just have to like slam the escape key. So basically, every time I create a new component, or a new list or something like that, that asks me for a type like this, it's really annoying, but you have to hit like the escape key every time. So this is our data tree for eventual output. Currently, it's empty, or it might be filled with zeros, depending on how that works. So this is sort of our setup. So I like to put a little like barrier between chunks of my code in these script editors, just so I can see different areas of the code a little clearer. Okay, so currently this is still doing nothing. You know, it's not outputting anything. But we know in the end we're going to output the output data tree. So I might as well say A equals output here, and that's just at the bottom. Some space to write, because I know that this is what we're going to be adding to and then outputting at the end. So first, we are going to create the first row, which is an int array filled randomly with zeros and ones. Okay, so how are we going to do this? First off, we need to create that int array for the first row. So we're going to say int array first row new int array, and it's going to be of a size x, because that is our integer x. That is our x size of the grid that we want. So each row is going to be of length x. So I say new int x, and capitalization is important. I'm going to be using x and y as capitals to be like the size of the grid, but we will definitely have some variables x and y lowercase. So don't get those mixed up. This is a capital X, and this should be a capital X and a capital Y, not a lowercase x and a lowercase y. Capitalization matters. Okay, so we've got this empty integer array, or we know it's actually full of zeros from last time. But what we're going to do is use another loop to fill that array, right? So for int I equals 0, I is less than x, capital X, the size of it, I plus plus. This means we are going to loop through x number of things, so one row's worth of numbers. Now what we're going to do is set an if statement. So we're going to check, this is where we're going to use our random number for. If rand dot next double, this is a decimal number from 0 to 1, so like 0.35, 0.5, 0.75, or 1 or 0. So if rand dot next double is less than chance, and then we open our brackets, or whatever those are called, the curly braces. So if it is less than chance, so we set chance to say 0.5, so there's an equal chance of it being less or higher than that number, we're going to say first row I equals 1. Okay, and then we're going to say else, put in that little 2 curly braces there to make this else. We're going to say first row I 0. So basically this is saying, it's over here. We've got our chance here on the left. This could be, if I set it to be 0.5, there's a 50% chance that each of these numbers, there's a 50% chance for each cell to be 0 or 1. If I set it to be higher, like 0.8, there's going to be more ones than zeros. If I set it lower, there's going to be more zeros than ones. And then all we have to do now is say output dot add range, because we're adding an entire row at once, not just one item. we're going to say add range first row, the whole first row, and then it's asking you for a GH path. So this is basically the way that you address items in a data tree in Grasshopper. So you've seen like the curly braces and then like 0, semicolon 0, or like maybe multiple levels. This is how you like set the address. So where in the data tree are we putting this? Because it's the first thing, we can just say new GH underscore path. Very annoying to type that. New GH path 0. That's all. So output.add range, we're adding the first row, and where are we adding it? To this new GH path that we just created. White space, no reason for it. Okay. And now when I hit OK, you can see we've got, actually I should make this X much smaller. So if I set X to 10, this is only a 10 width row. You can see I have 10 items, and chance, if I turn chance lower, more of them are zeros. If I turn chance higher, more of them are ones. That's because we are checking for each number in the row whether it becomes a 0 or 1 based on this chance. So this is like our percentage of zeros and ones. And then obviously I can also set the seed to change it, and that will change the position of those. So if I keep it at 0.5 for now, there's an equal chance for things to be 0 and 1, and I can change the seed to get different inputs for this. Okay. Now, we're going to need to go, well, first, I guess I will copy all this, add 1, because we're done with that. So that was initializing the first row. Okay, so maybe I'll group this and name it initializing, and then I will disable it just because there's no reason to have it. I've got it down here. All right, now we're going to need to jump into that file I supplied you guys with. For me, it's called for participants. I'm not sure, you guys it might be called something else. So I don't know if you took a look in here, but it's just 2 little C# script components. Mike put a link to this file in the chat, I know. So if you don't have this file, get it right now. And what we need to do is jump into this first one. And it just has this like block of code that is just kind of annoying to type. And it's really important to not get wrong. So I just supplied it to you guys. So you can just highlight it off, copy, just copy this, all of it, okay? From this bracket up. Copy that, hit OK, whatever. Jump back to the original thing. And in our original file here, we're going to jump into this one that we did. And down in the custom additional code area, this is where we're heading in now. Let me zoom in, sorry guys. In the custom additional code. So right now we've been writing in the main area here, but we're actually going to jump down to the custom additional code. This is the cool zone. And we're going to paste that. Just paste that. And this is the what is called the Wolfram rules, or I guess Stephen Wolfram really got to put his name on this. But all this is going to do, this is going to be a function that we're going to use to return the next generation of the cell B with neighbors A and C. So we have our center cell, we have the neighbor to the left, and the neighbor to the right. And we're just going to abstract that into this function here. But don't worry about that right now. Basically, this is the same thing as what we were doing. Okay, this is the same thing as what we were doing right here. Now I need to show you more in my Rhino window. Well, I don't feel like changing the window size. It's basically telling me like how to react when I have these different neighbor configurations. So that's what we add that for. All right. So jumping back in to our code. We've got that first row nicely done. So what I'm going to do is actually put a little barrier just so I can have different sections of the code. Oops, got to zoom in, can't forget. All right, so put that there. And then I'm going to make some space to write some more stuff. And here's the main thing that we're going to be doing, right? We need to now, we have that first row. We need to have another way to, we need to be able to generate that next row. And then we need to have another way to generate the row after that, and the row after that, and keep adding that to the data tree that we have. So we've got that first row. but we need to have a way to get to that next row and move on, because there's going to be y amount of rows, right? We have x length row, and there's going to be y number of rows. So what we're actually going to do is create a second int array for switching the current row to the next row as we go. So this is pretty common in coding. I'm gonna maybe stop acting like you guys don't know anything about C# and probably just focus on the cellular automata stuff, you know, because at this point I feel like you have to know. Okay, so we're going to create an int array current, and that's going to be equal to first row, right? So we started off by saying this int array is that first row we just created, and we're going to call it current. And now instead of saying output.addRange first row, what I'm actually going to change this to say is output.addRange current. So just add that current row, which is the same as that first row. Then we're going to say go through each row, generating the next row based on the current row. So the basics of this one-dimensional cellular automata, right? We're going through each row, generating that next row based on the current row. So how are we going to do that? Well, if we're going through each row, we're going to need a for loop, right? So we're going to say int I equals 1, not 0 this time, because we already have that first row done. So we're going to say int I equals 1. I is less than y, the capital Y, aka the amount of rows we have, right? So for every row, int I equals 1, I is less than y, I plus plus. And in this loop, what are we going to do? We're going to say, well, we want to generate and add the next row to the output data tree. How will this work? We don't have a way to do that yet, right? Well, I want it to look something like this. I just want to call a simple function, right? I want to say something like generate, and then put in like the x, the current row, and the rule set. Those will be the inputs for this function. But we don't have this function yet. But this is what we want, basically right here. And currently, if I close this, this is doing nothing different than what this was doing. But we're like all set up to start our main function in there. But before we do that, I'd like to visualize it more than just using the panel here. So what I'm actually going to do is resize my windows to be even. And I'm going to leave this, file, just so you guys can see this. You guys can use this. All right, great. Because I'm going to be tired of looking at zeros and ones in a panel. I want to see like squares or something on my screen. And the way that we're going to do that is we're going to get a square component, the square grid component, not the square number component, you know. We're going to take the x input, put it into the extent x, and the y into the extent y, just like that. Here, I'll move these up so you can see. Okay, so now we've got our grid. That's a wonky grid. Make it a little paper size. I will actually turn off my grid and split axis. Okay, great. So we've got that, and the cells are arranged in a data tree. There's no reason for it to be this 3-deep data tree if you mouse over the cells output. So I'm just going to simplify it. I really don't know why it comes out like that. I hate that. It can be simplified. So there's 44 rows or whatever. In this case, there's 44 rows of 58 cells or whatever. But I want to be the opposite. So I'm going to reverse this, then add a flip matrix component. So this will change all x's to y's and y's to x's in this. This is just for visualizing. If we don't do this, you know, we want our one-dimensional cellular automata to go from top to bottom. But if we don't flip the matrix and reverse it, it goes from bottom to top. So it's just for visualization purposes. This isn't like something crazy. Then we'll get a dispatch. oh no, sorry, a total pattern component. And the list is going to be these cells, and the pattern is going to be from our component there. And if I take this off, you can see that the initial row is just repeated throughout, and that's perfectly fine. So we can visualize at least now this initial row is on, off, 5 ons, 4 offs, 2 ons, whatever, whatever. And if I put a panel coming out of this, you'll see it is 3 offs, 2 ons. So I guess there was an invisible 3 before this. 2 ons, so there's 1, 1, then there's 1, 0, and then there's 5 ones, 1, 2, 3, 4, 5, and then there's 4 zeros, I'm sure. And so that's how this initial row will look. Okay, so we have certain cells that are on, certain cells that are off, and now we've got this whole matrix, but it just repeats. So what we now need to do is create every generation so that it's not just repeating that first row every time. So I can delete this panel because we know that it's working as it should. And we're going to dive into the code and write our basically main function that is going to do like everything. And I don't know, I didn't mention this, but we're going to have like little sections here. You know, we have the 1D, then we're going to have 2D, and we'll take like a little 5-minute break between each one or something like that, so that anyone who is confused by anything in that section can ask me questions. And interestingly enough, the one-dimensional cellular automata I think is the hardest to code. And then it doesn't really build on it to make the 2D cellular automata, but the 3D cellular automata really easily builds off of the 2D cellular automata. So just interesting to say. All right, so we've got this make-believe function that we want to use to generate that next row. But since we don't have that function yet, we got to go create it. And you create functions down here in the custom additional code. So I just copied that barrier thing that I made, and I'm just going to, so I can separate my functions nicely. Give myself some room to type, and I just like to do that. All right, so now we've got this idea of we need to generate the next row using the current row in the rule set, okay? So what we're going to do, make a comment, this is going to be the process of creating next generation. Process of creating the next generation. It's going to use the current row and the rule set to create the next row. Easy peasy. And what we know is that each row is an integer array, so we know that what we're going to want from this is an integer array. So we're going to call this function public int array generate. I put a capital G. I don't know what the coding preferred thing is, if functions should have capitals or not. I know it's different in different languages, but it doesn't actually matter. But I put a capital. So it's going to take an int x, it's going to take in an int array, current row. It's going to take in a list of ints, rule set. And you may be thinking, eagle-eyed watchers will know, why is the list of ints and not an array of ints, right? Don't worry that this is red. Because, you know, here we create this as a int array, not a list. Well, Grasshopper converts it to a list, so when I put it into this, it is a list. So we have to expect it as a list instead of an integer array. But for Grasshopper purposes, it's the same thing. When you're outside of the C# component, it's the same thing. Okay, so we're going to create an integer array in this function. So I might as well say, for output, we're going to have an integer array, because I know this is what we're going to be outputting. I'm going to call it next, because we have current. I'm going to call this next. That's going to equal a new integer array. Oops. New integer array of size x. Okay. So this will be what we're going to output at the end of this function, an integer array called next. All right. So the main meat of this function, sorry, for every cell in the row, at its neighborhood and examine the states. This determines the next state of that cell. Okay? And also, we're going to make sure we wrap around edges. That's important, because if you don't wrap around edges, when you get to the edge of your grid, it's going to do some sort of weird stuff. Okay, so since we're doing for every cell in the row, we need to have a for loop. For int I, 0 I is less than x, I plus plus, big X. We're going to need to keep track of the states of our left neighbor, our self, and our right neighbor. So we're going to create some integer variables here. Int left, center right. So these are just 0 right now. These are not instantiated. And we got to look at every state. We got to look at the neighbors. We have to consider what their states are. So how do we do that? Right? We say for the left neighbor, if we're looking at every cell, left neighbor is going to equal current row, and the index is going to be I minus 1, because it's the one before it in the index. It's the one to the left of it. All this. Then we have our center, and that is just going to be equal to current row I. That's the current index. I'll call this center. Then we have right, and that's going to equal current row, you guessed it, I plus 1. So left is I minus 1. The current one is just I. And the one to the right is I plus 1. So we're looking at the list and then the neighbors in that list. I'll call this right neighbor. And that's good. But like I said before, what if you're that first cell? Your left neighbor, I minus 1, 0 minus 1 is negative 1. But there's no index negative 1. So we have to make sure we can handle the wraparound. Space that. So we have to make sure we handle the wraparounds for the cells indexes. Okay, so if you are that first cell, we're going to say if I equals 0, we have to do a little special for that left neighbor, don't we? So left equals current row x minus 1. So this is going to get the last cell in the row. So instead of being I minus 1, it's x minus 1, because x is the total length, and we get that last index by saying minus 1. So this is the left neighbor wrapped to rightmost cell. I'm just going to say wrapped to rightmost. Center is still current row I, and right is still current row I plus 1. I'm just going to label these. And the reason for that is because if you're that first cell, your right neighbor is still just the second one. But your left neighbor has to be the one all the way on the other side. Right neighbor. Okay, so we've got that first cell, but then we also have to handle that last cell, because if you're that rightmost cell, your right neighbor is now the first cell, all the way wrapped around at the beginning. So we'll say else if I equals x minus 1. That's saying if the index is the last index. Now we say left equals current row I minus 1, because there's no problem with that index. You're all the way on the right. So your left neighbor is just that second last one. So we just call that left neighbor. Center is still just yourself. And right is current row 0, that first cell. So center, right neighbor, wrapped to leftmost. So this is how you handle these wraparounds. And then we'll just say else, if it's not the first or last one, you just treat it normally. Did I need that? No. Yes. Okay. So we can handle the wraparounds now. So we're going to look at each cell in the row. If it's that first cell, we're going to check its left neighbor, which is the one all the way on the right. We're going to check itself. We're going to check its right neighbor. If it's the last cell in the row, we're going to check its left neighbor, itself, and its right neighbor, which is now wrapped around to that first cell. And any other cell, we can just check the one to the left, itself, and the one to the right with no issues in the indices. Okay, so that's like the hardest code for this whole thing right there. That's not even that bad. And now we're going to use this function here, the rules function that we copy pasted it. We're gonna use that right now. We're going to compute generation cell state based on the rule set. How are we going to do that? We're going to say next I equals rules, which is that function that we have up here, rules. Next I equals rules, and then in there, what is it expecting? It expects the rule set. It expects the left cell, it expects the center cell, and it expects the right cell. So basically, since we have assigned these to be the numbers from the states of the cells, we just put this in, and then this is going to give us, in our integer array here, the correct state for the next generation of that cell. Then we can close the for loop there. And we can say, one last thing, we have to change the current row into the next row. That way we can just loop through this and fill out the entire grid. So this is just going to be a short little loop for int I equals 0, I is less than x, I plus plus. And this is just going to be current row, I equals next I. So that's just like replacing every value in the current row with the next value, just so that when we run this function again, we can move on and not just get stuck on the same row. And then we'll say return next, and that is our main function here of generating the entire thing at once, of generating each row based on the next row. And then all we have to do is come up here and basically input this into our placeholder loop here, where we had how will this work generate. So in there, we just say this. Output.add range. And inside that, we're going to say we're going to use our generate function. We're going to put in the x. We're going to put in the current row, which is just current named here. Then we're going to put in the rule set. Then we have to tell it where in the data tree that's getting put into. So we're going to say new gh path I. So that's what we're in this for loop here. Okay, so let's check if this worked. Okay. Ooh, look at that. So based on the rule that we have, we should be getting all sorts of different effects. Or basically, we have this initial row, and then it moves down to the next row and checks the cell states, and moves out to the next row, and moves out to the next row. And based on the different rule you put in, you should be getting all these different things. So this is basically done. If you put in rule 30, you'll be getting these triangular shapes, and you can change the seed, and you can change the chance also. So that if I move this lower, there's less and less on cells in that first row, and you can see how that affects it as it goes. If you wanted to look at this nicer, you could say boundary surfaces, but this is going to be a little slow, kind of, just so you can like see them colored in, right? That's very cool. So you can see our result here. So is anyone not getting that or getting a error? You need to probably check that you have all your all of these correct. You might be getting like an index out of bounds if you didn't set these correct, because it's trying to check like index -1 or index more than the amount that there are in the row, things like that. But that is our one-dimensional cellular automata, basically completed. But one thing that's cool, this is a little slow, right? This is 73 milliseconds to visualize these as planar surfaces or whatever. I'm going to show you a cool little thing that I discovered to draw these in a cooler way. So take these cells, rectangles. We're going to make a new C# component. We only need one input. I'm going to call it rects. And it's going to take in a list of rectangles. So we're going to right-click and change this to list access. Then we're going to change this to rectangle 3D. We're going to take this, put that in there. Since that's a tree, we're actually going to flatten that input there because we just need the list. We just need all of them at once, not a tree. And we're going to jump in. I'm not really going to explain this code because this is just like a little visual thing. It's not related to the cellular automata. This is just a cool thing to do. So just follow along if you want to do this. This is just a cool little item here. We're actually going to start off by making a new mesh called joined mesh because this is going to be what our output is. Joined mesh equals new mesh. Then we're going to create a list of meshes. List mesh M list, I'm going to call it. Equals new list mesh. All right, so we've got an empty list. Then we're going to loop through every rectangle. For int I equals 0, I is less than rex dot count I plus plus. We're going to say mesh M equals new mesh. Then we're going to basically say what we're doing in this is we're going to be looking at every rectangle and we're going to create a mesh face for every rectangle, or like a simple mesh that is just like the 4 vertices comprised its quad face for every one of those rectangles. So we're going to say for int j equals 0, so we're nesting inside of this other loop. J is less than 4, j plus plus, and it's 4 because there's 4 corners in each of these rectangles. So then we say m dot vertices dot add rects I dot corner j. So for every rectangle, look at each of its 4 corners, add that as a vertice to this mesh. Oops. Corner should be parentheses, not brackets like I had it. So vertices add for each rectangle all of its corners as vertices. So that's that little subloop. Then we're going to say mesh face f equals new mesh face and 0, 1, 2, 3. Then we're going to say m dot faces dot add face f. So we're adding that face to this mesh that we created. So we have now vertices in that mesh and a face in that mesh. It's really annoying how you have to create meshes in Grasshopper. And then we're going to add that mesh to the M list by saying mlist.add m. Okay. Now out of this loop, we can say joined mesh.append mlist. So we're going to add now all those little meshes to this joined mesh. This is like joining them. Then we're going to do magic. Ready for this? Polyline array equals joined mesh dot get naked edges. So we're going to get all the naked edges of this mesh that we just created in here. And then we're going to say A equals edges. What we're going to get is something very cool. So if I now unpreview this, this is the output of that. We get like all the cells sort of joined along their edges in a really cool way. And it turns out, look at this, there's only 10 curves here. So it really, like, if you were going to say plot this or carve it with a CNC or laser cut it, this reduces the number of individual like strokes you'd have to make. And also very cool is if now I put the fillet component in there, set the radius to 1, put that on there, then I unpreview that. Now you got something really cool. This is like a nice joined curve. And now I can come back to the seed. I can change the seed. You can see all sorts of different patterns. And if I change the rule, I get all sorts of different cool things coming out of this component. And it's just like a cool way to visualize that. Look at that. That's crazy. How many curves is that? Sometimes you're really surprised and it's like only like 2. So this is only 11 curves. Very cool component that we just made. So this is just, I don't know, I call this grid join. So maybe I'll put component dot message equals grid join. And this is just something that I found while I was trying to do this, and I found this like weird trick where you can use meshes to do that. Grid join. Okay. So that's a cool way to visualize the 1D cellular automata. I just like it more than like looking at this. I don't like looking at that. It's not that nice to look at. I think it looks cooler when you have it like this. Or if you fill it in with like color or something like that for each of the cells. All right. So we've done this. Mark Foxworth, I see your question in the QA. When we get to a stopping point, can you either upload your components or leave the screens open? I have a typo somewhere. Yes, I can do that. But I guess I'll do that now, actually, because I gotta go pee. So let me put this in here. You probably have a typo in this section, I'm going to guess. And we can go for a little bathroom break or something. And then get some water, go to the bathroom. And anyone who has some issues, maybe put them in the chat and check out my screen while we take this little break. And then we're going to, when we come back, we're going to edit this code to be the 5 neighbor version. So instead of 256 rules, we will quickly have like 4 billion something rules. So that's what we're going to do when we come back. But here it is. How can I share the current script in the chat? Mike, you know if it's possible for me to quickly save this and like send it to you? Well, just the C#, probably not, but I might be able to upload the whole GH file so far. Say it again.
You can put the GH file into the chat.
Oh, really? Okay, just by dragging it or whatever?
Yeah, you can just drop it in.
1DA. I called it 1DA, and I'll put that into the chat. Oh, great. Yep, okay. So there it is, guys. So that's the complete thing, but we're still going to do a bathroom break. I've been drinking a lot of water. So see you guys here at 12:35. Okay, I'm back, but I'll wait for everyone to come back. It's a 5-minute break, but if anybody has any questions or anything, I can answer them right now. Questions or comments, I guess. Hey, can you post that file again? I was showing on my iPad. You don't see the chat? All right, no worries. Also, Dylan, your messages are just to hosts and panelists in case you wanted to talk to him. But yeah, if anyone has a question or comment, I can talk now. One of my favorite rules is Rule 106. It's a pretty cool rule, especially when you do this grid join thing, because you get all these like checkerboard patterns, and it's really, really satisfying to see a plotter draw this because it like meanders all throughout that, all those things. Here, let's pump this up. Really get a feel for patterns here. Pretty cool. Change the chance. Not that cool. So a lot of rules actually become less cool. Is the file supposed to show up in the chat? You don't see any? Really? I think everyone else does. It's weird. You got it. Well, Dylan, you're in luck because we're friends. So why don't you just hop on Discord? I'll just send it to you there. You get the special treatment. This is only because we're on a break right now. There you go. Dylan, I sent that to you over Discord. All right. I guess one more minute on the break. Something like that. Some pretty cool rules. I think like 150 is pretty cool. Yeah, 150 is kind of cool. You get these triangles. A lot of them, you'll see that there's these like repeating triangles patterns that occurs a lot in elementary automata. I think 110 is another cool rule. Maybe not. 116. Very strange. You guys can't see the GH panel, but some other people can. How does that work? Javier, it's right above your comment there. Okay. All right. It's been 5 minutes. Maybe you need to switch chat to everyone. Okay. All right. It's been 5 minutes. We are. I'm gonna move this small. It's been 5 minutes. Hope everyone had a really good break. Let's get back to it. So what we're gonna do now, we've basically completed. So I can put this in a group. I'll call this 1D. 3 neighbor CA. 1D 3N CA. And that is like our completed code for this basic one-dimensional cellular automata. And now what we're going to do is change from 3 neighbors to 5 neighbors. So we're going to get way more variety in our patterns that we get out of this. Instead of just 256 rules, we're going to have 4.2 billion rules, which is like way crazier. But of course, if that's the case, we need to change our rule set generator because this is relying on there being only 8 configurations of the neighbors. So what we're going to do is make a new version of this. So actually, I'm going to disable all this. And we're going to just start with a new C# script component because we're going to do this in a little bit of a different way than that first one. So instead of modifying the 3 neighbor rule set generator, we're going to just start from scratch, basically. What we're going to do is get rid of one of the inputs. We only need one. We're going to change this to say seed. It's going to be an item access, and it's going to be an integer. So it's a little different than starting with the rule. And the reason for this is we can make a slider from 0 to 255, no problem. But what if you want to make a slider in Grasshopper from 0 to 4 billion? It turns out you can't, and the highest number you can do in Grasshopper is 1 million for sliders. You can't make a slider that's larger than that. I mean, you kind of can. Like if I do that, But if I go to edit it at all, and then I bring it back, it turns it down to 1 million. So we can only do 0 to 1 million, but there's 4 billion rules, right? So how can we use this? We don't want to just get rules 0 to 1 million. Like I don't want to be only in that first little bit of the rule space, I'm going to call it, right? There's so many rules in here from 0 to 4 billion. I don't want to be restricted to only seeing rules from 0 to 1 million, okay? But what I can at least do is say, all right, well, I have a chance to see any of these rules, like 1 million different rules throughout the rule space. So we're going to use 0 to 1 million as a seed slider for this. We're going to use random numbers to help us explore more of that rule space. What I'm saying will make sense in a second. Okay. All right. So I'm gonna dive in here. New component we've got, and I'm gonna make a component message equals 5n capitalized 5, huh? 5n rule set generator. So this is the 5 neighbor rule set generator. So it's going to work a lot differently. Not a lot, but it's going to work differently than the 3 neighbor rule set generator. So we know that there are 2 to the power of 5 equals 32 possible neighbor configurations of a 5-cell neighborhood, right? We know that there's that many possible neighbor configurations, 32. That is 2 to the power of 32 equals 4,294,967,296. So that's way more than 256, obviously. The issue, sliders in GH only go to 1 million. So we can use random numbers to help us generate this. Okay. How are we going to do this? Well, we're going to first make our random. That's obviously going to be needed. Equals a new random. Put the seed into it. And then we're going to be using something called a long. So currently we've been using int32 numbers, and there's like an upper limit on those, and I think it's around 2 billion. So int32 can only generate numbers between like -2 billion and 2 billion. And if you go higher than that, you'll say like int32, I don't know, it'll give you an error because you can't create a number that big using that data type. So we actually have to use a different data type. And what that is called is a long. A long is like, you know, we have ints, we have doubles, right? Ints are integers, doubles are decimal numbers. A long is like a very big int, so you can have a much larger number. So 4 billion is inside the range of the long. So we're going to create one long called min. That's going to be 0 because the first rule is 0, and then it goes up to 4 billion. So the minimum is going to be 0, and we're going to make long max. That's going to equal 4294967,295, right? So one less number than the amount of rules. That's because we start at 0. So there's still this many rules. It's just, this is the index, basically. So just make sure this number is one less than this number. 429,496,7295. Yes. Then we're going to say, all right, we got to get a rule from this, right? So this is just generating that. Yeah, I think longs are only whole numbers. I'm pretty sure. Yeah, good question, Jerome. So basically, we have to do some steps to create the rule. First, in our first one, we could make a slider from 0 to 256, right? But here we have like an additional step where we have to generate a number between 0 and 4 billion something first, just to get that rule number. Then we have to then decompose that into binary. So first things first, we have to create our rule number, which is like already sort of a challenge because of such how big that number is. And we're going to write a function. and it's going to be called long random. Long random. And that's going to take in our min, our max, and our random. This is not written yet, so I'm going to comment set. We don't have this function yet. So this is just to generate that, that rule number. So come down to the custom additional code, give yourself some space to write. We're going to create a function that gives us a random long number in a range. Random long number in a range. And so we know our range is going to be from min to max, etc. So it's going to return a long. We call long random. We take in long min, long max, and random rand. Okay. Now this is not some code that I wrote. I took this from Stack Overflow, so it's going to be kind of, it's like a little hacky in my mind. So we're going to actually create a byte array. We're going to call it BUF for buffer equals new byte array size 8. Okay. We're going to say rand.next bytes and input that byte array buffer, right? So BUF. Then we're going to say long rand equals bit converter. What this is, don't ask me, I don't know. .to int 64, okay, and then buff, comma 0. Okay. So whatever that's doing, a little hacky. I'm not, I can't explain it line by line, but just know that this works to create a long number in a range you give it. And then we're going to say return parentheses math dot absolute value, right? Abs of long rand, that number. We're going to use the percent sign to mean modulo, so long rand modulo parentheses max minus min parentheses close parentheses plus min. If you've ever done anything where you're generating a random number in a range, this percent, this part of it might look familiar to you, where you're doing like number modulo max minus min plus min. This is just a way to generate a number in a range, basically. But this whole function here will create a random long number in a range you give it. So I can now uncomment this because we built out that function there. So that's really good. So now we finally have our rule number, and this should be, let me see, can I even export that as a long, or will it complain? Nice. So what you can see here is I have a slider from 0 to 1 million, and it allows me to create a random assortment of numbers in this range from 0 to 4 billion. So we're effectively getting 1 million random rules inside of our 4 billion sized rule space. And that's better than only being able to see rules 0 to 1 million. I can at least now see a wide scattering of rules. So one thing that you guys could seek to improve after this webinar is done is maybe you could have some way where you can really be sure you can generate all 4 billion rules. Because currently this is only a 1 million sized subset of that 4 billion. So not even that good, but at least lets us see a scattering of rules around the rule space instead of just the first 1 million rules, because that's the limitation of the slider in Grasshopper. Okay, now what we're going to do is going to look quite familiar. Oops. Okay, so now that we have our rule as a number, we're going to get the binary representation of that number added left to 32 digits. So last time we were padding left to 8 digits, but there's 32 possible neighbor configurations, so we need to pad left to 32 digits as a string. This is going to look familiar. String binary equals convert.toString number with the to formatter to make it binary dot pad left size 32 comma, and then use the 0 character as your filler. And we're going to say int array rule set, just like last time, equals new int array of size 32, because we know that there's going to be 32 numbers in this rule set. Then we're going to say convert each character in the string to an int and add it to the array. This is the same code that we did last time, basically just slightly different because there's 32 numbers. So for int I equals 0, I is less than 32, I plus plus. Another temp int, familiar to you? Int dot try parse each of the numbers in that 32-digit thing. Or sorry, not 30 digits. Yeah, actually it is 30 digits. My bad. Binary I dot to string, just like last time. Comma out temp. So we pass that integer out to the temporary variable we created, and we say rule set I equals temp. And A is going to equal rule set. And we're going to actually add a second output, B, just so we can see what the rule is. This is so that, because we're not supplying this with a rule, we're supplying with a random seed. So we can generate that rule inside this component, right? So we want to be able to actually see what that rule is. What do we have here? The name B does not exist in the current context. That's because I haven't added a B output yet. So we can see our 32-digit long rule set, but also we can get the rule number itself. And this is useful for, like, if you find a cool rule, you can save this number, and it's a little easier than saving the binary representation of that number. You can just like add a data recorder component to this output. Okay, so really the only difference in this and the other 3-neighbor rule set generator is that this has the additional step of having to generate this rule number inside the component, because sliders in GH only go up to 1 million. So we've got this completed now. So this is our 5-neighbor rule set generator. Took a little bit of coding, but we got there. Okay. Now I'm going to grab the original. Can you decimal and multiply by 1,000? I'm not sure. Maybe it could be a good way to do it if that works. Now what we're going to do is take our regular 3-neighbor code that we just finished up here and all its inputs, except for the rule set one. Copy that, bring it down. Okay, so this is our 3-neighbor code, right? It's complaining. What we're going to do is I'm going to copy our 5-neighbor rule set generator, and I'm just going to plug that in. It's not going to work correctly, obviously, because this is expecting only 8 possible digits in the rule set string, where this is giving us 32 digits in the rule set string. But we can quickly fix this. And this will go from the 3-neighbor version to the 5-neighbor version in the blink of an eye, pretty fast. But first, we have to go into the file I supplied you guys with and jump into that second one. And you can see why I didn't want us to have to type this on the webinar live. Like, this would really suck to type this. So this is the all 32 combinations of 5 neighbors, and it's so annoying to type this because if you get one of these numbers wrong, it's going to be completely incorrect. So I've done that annoying stuff for you. So just grab all that code, jump back in, double click on this, and replace this block with the new block, all 32. It's going to error, obviously, because it's still using all the old code, expecting like 8 digits, only 3 neighbors, stuff like that. But now that we have that all in there, we can modify the code to accept our new 5-neighbor set. All right. How are we going to do it? Most of it is the same, actually. Most of the code is the same. So I don't actually have to change anything in this. We only need to worry about this code down here. I now need to have a bit more code in this section here, where we're checking the neighbors. We're not just going to have a left neighbor, a center, and a right neighbor, right? Because we're checking 2 to the left and 2 to the right now. So there's 5 neighbors. So what I'm going to put in here is I'm going to call it 2 left, left, center, right, and 2 right. Okay. I wish I could just say 2 left, but Sharp doesn't like it when you start a variable with a number. So that's what I'm going to call it. 2 left, left, center, right, 2 right. So that is now our new neighborhood. We're checking 5. Okay. We now have to handle the wraparounds in a different way here because now we have more cells to consider. So this is going to be a little tedious, but I'll explain it as we go. But it's definitely very necessary. So let me just put a little thing here. This is the first cell. So we have to handle the first cell's neighborhood specially. We have to handle the last cell's neighborhood. And then this is every other cell. But we also are going to need to worry about the second cell and the second to last cell, because now our neighborhood extends further. But first off, let's just update these, because now we have left, center, right, but we're missing 2 left and 2 right, right? So if it's the first cell, 2 left is going to be the current row x minus 2, right? So that is going to be the 2 to the left wrapped rightmost minus 1. Okay? Does that make sense to you? This is, since we're looking 2 to the left, we have to wrap around even further. And then we're going to say 2 right equals current row I plus 2. That is our 2 to the right neighbor. Okay? And we're going to have to do this for each of these special cases, okay? So for the last cell, our 2 left neighbor is going to equal current row I minus 2. And that is our 2 to the left neighbor. And our 2 right is going to be current row 1. So that's that second cell, right? So this is the 2 to the right neighbor wrapped to leftmost plus 1. So this is the second cell in the row. And we're going to have to do it here too. 2 left equals current row I minus 2. This is for any other case besides the special ones that we have to handle, so there's no problem here. 2 to the left neighbor. Call this 2 right. Current row I plus 2. That's 2 to the right neighbor. Okay, so we've updated all of those. Just don't forget your semicolon. Maybe I can clean up these comments. It's just nice to be able to see which things you're talking about, I think, when you have these labels like this. You don't need to label them like this, but I like to. But okay, we've got our first cell, we handle that. We handle our last cell case. We handle every other case where it's normal. But you know what we actually need to do is handle the second cell and the second to last cell, because those are going to need to wrap around as well, unfortunately. So what we can do here is press enter, make another else if statement. Wow, where am I going with this? Why is that so ugly? There we go. Else if I equals 1. I equals 1, right? This is the second cell, okay? And what we're going to need to do is copy this first cell 1 into this, all of those. So we can save some time by typing. And you only need to adjust the 2 left and left one, okay? So 2 left is now just x minus 1, and then left is I minus 1. So this is now just the left neighbor, and this is to the left neighbor, wrapped to rightmost. So I hope this is making sense to you guys. It's pretty logical. That second cell is looking to the left, right? So it's going to be that first cell, but then all the way on the right also. And then we're going to do the same thing for the second to last cell. So let me put that down here. We'll put if I equals x minus 2, and this is the second last cell. And if we're looking at the second to last cell, right, we're looking 2 neighbors to the right. That's going to be that first cell. So we have to handle that wraparound also. So what we can do is copy all the last cell code, pop that in there. Second to last cell, to the left is fine, left neighbor is fine, center is fine. Right neighbor shouldn't be 0. Now it can just be I plus 1. And then current row, 2 to the right is going to be current row index 0, that first neighbor. So it's just right to leftmost. Okay, so this is kind of a lot of tedious, similar code. So I hope you didn't get lost there. But that's literally basically all that we need to do to adjust our code to handle 5 neighbors instead of 3. The only other thing we need to do now is add in the rules thing. To left, left, center, right, to right. And if I'm not forgetting something, I think that's all we need to do. So why don't I hit OK? Okay, we're not getting any errors. That's great. In that case, I'm going to pull in all this stuff. Hook it up so we can visualize it. Okay. Hook your extents up correctly. Call pattern, come from here. All right, I'm gonna hit save before I do this, just in case. Nice, look at that. All right, so let me check this out. When I change the seed, yep, and I can change my rule. Got all sorts of funky, cool rules. Maybe I should up these way more. I want to see it bigger. Yeah. Now you're getting so many different types of things because we're considering 5 neighbors. So we're getting all sorts of different, more complex rules than the original 256. So this is your full-on 5 neighbor, 1-dimensional, 2-state cellular automata. You get a lot of different rules here. And see, one thing that I really don't like is when you drag a slider in GH, it will show you like one intermediate step there before it moves to your final number. You see how every time I drag this, it will generate 1, and then it will go to my number that I drag it to. And I just cannot stand when I see a really cool rule in the middle of it, and I don't know what that number was. And it's like, that was really cool. I wish I could see what that number was. So we're actually going to change our rule set generator from taking in this seed number like this to just having a button that we can click. That way I can randomly generate a new rule with 1 button click, and it's not going to show me an intermediate, like another rule as it loads the next rule, which I just can't stand. So we're going to delete that. I'm going to change this to say step. And we're actually going to change it to be a Boolean. And we're going to put a button connected. And this is quick. This is just a little thing that I like to do. Now what I'm going to have down in the custom code, sorry, let me zoom. Don't need to make it small for you guys. This random, right? We are going to delete that. We're going to put it down here. We're going to say random rand equals new random with no seed, because now we don't have that seed input. And then we're going to come up to this long rule equals long random, right? We're going to get rid of the type declaration there, because what we're going to do is actually create this initially down here. Long rule equals new long, okay? Then we're also going to add int array rule set. So we're just declaring these variables and things down here first. And so obviously you can also get rid of the type declaration on that right there. And the reason we're doing this is that they're persistent throughout the reset process, basically. So now all we can do is if step, and then lock all of this inside of these brackets. So now whenever I click the button, it's going to set long min to 0. It's going to do this. It's going to set the rule to a new long random. It's going to create the new rule set. It's going to do all this, but only when I click the button. So if I click that button, oops, I made a mistake. The type or namespace long cannot be found. Oh, line 92. I should not have capitalized this L. Okay, so here's the cool thing, right? Now I click the button, it creates one new rule. And I'm not going to have to slide that slider around when it's really slow and lagging because I'm trying to make a 1000 by 1000 grid or something like that. And I see a cool rule as it loads that next position on the slider, but I don't know what that number was. Now you can just click the button and get a new rule this way. And since it's all random anyways, you're just moving that slider for the seed around randomly. This is just as good, and it's better because you don't waste computing on a rule that you're just going to skip over. I don't know why the sliders do that. I really hate that they do that. But this is like one way you can get around that. So now our rule set generator works with just a click of a button. It will generate a new rule for you. You can see what that rule is there, and you can see the output of that in the window. There is actually some other cool things you can do. I come back to the end of this and see the curves we've got here, right? A lot of times you'll get like one really long connected curve from doing this grid join operation. And what I like to do sometimes, especially for plotting, it's cool to see that singular curve colored differently. So I'll get a curve component and just plug that into there, and I'll say get the length component. Measure the length of each of those curves. Get the sort component, sort list. Use the length as the sortable key. The curves are the values that we're sorting. So basically, we're sorting these curves by their length. I'm going to reverse the values output because then I get the longest curve first instead of the shortest curve first. Then I will get a split list component, set the index to 1, plug that in there. Then if you have human, you can do this. Otherwise, this is just the custom preview line weights component for human. This is just for visuals. So this is if you don't have this, you're not missing out on much. I'm just showing you a cool way to visualize things. I'll set this to be, what is this? Bank or something. Shader. The geometry will be this one curve. Now go back, hide all these. Hang on. Don't worry. It's going to look good in a sec. I'll make the thickness like 3 or something so that it's easier to see. And then I will come down here, change the swatch to a different color, and color all the other curves that color. So now you can see this one pink curve, that is one single curve. And it is connected in a really long, circuitous manner. But it's really cool to visualize that, I think. Ugh, this gray colors, so gross. Okay, black, that's nice. So this is just a cool way to say, take that, color the longest curve differently. So that's what I'll say. Color the longest curve differently. And now if I hit seed, now we'll get some cool stuff going here. Wow, look at that. So it's like really weird and often unexpected how there's one like very, very long curve after the grid join operation. But it's pretty cool to see. So you can just hit the seed step button. And step 3 if it was like, look at this. This pink is one closed curve. And then there's only so many other solitary green curves. This pink that you're seeing here is one continuous closed curve. So if you were going to draw this with a pen plotter, it would not have to pick up the pen very much at all to draw this. So it's very satisfying to see get drawn. Okay, so I'm going to group all of that, and I'm going to call this 1D5NCA. And I will color it the same purple color as our last one. So we've got our one-dimensional 3-neighbor cellular automata, And now we have our one-dimensional 5-neighbor cellular automata. So that's really good. So we've got both of those, and now you have 4 billion rules to work with, and all sorts of things. So that's essentially the end of the first section of this. But I do want to point out a few things you could do to further explore it. So what else could you modify this to be, stuff that we're not going to tackle right now? Well, currently we're doing 2 states and 3 neighbors, or 2 states and 5 neighbors. But what if you modified this code to be 3 states, or 3 states, 5 neighbors? You guys probably cannot read this. 3 states, 3 neighbors. That's a cool thing you could do. Or you could do 3 states, 5 neighbors. And I've done those before in JavaScript. And when you get up to 3 states, 5 neighbors, the amount of rules that you can have is like a 110-digit number. So it becomes actually a big challenge in itself just to generate those rule numbers, because they are so huge. You can even say it out loud. There's so many different possibilities of rules you can have. And I'll tell you honestly, 3 states, 3 neighbors, you get some pretty cool stuff. But 3 states, 5 neighbors, it's mostly, you don't get too many interesting patterns for some reason. I'm not really sure why that is. But those are things you could adjust, or you could have as many states as you want, or more neighbors than that, or different neighbor configurations. So you have other neighbor configurations instead of just extending sideways, right? What if you did something like 3 neighbors plus the 1 from the row above that? And what I mean by that is if I have this cell, this cell, currently you look at to the left and right, and if you have an extended neighborhood, you look 1 more to the right and 1 more to the left. But what if you changed it so that you look at the neighborhood is shaped like this? So for this cell, you look at itself, its left neighbor, its right neighbor, and the previous generation. So you could have 4 states, 4 neighbors in that way, but in a different thing. What if you looked at it like this? What if you had uneven sides, right? And so for every cell, you're looking at this cell, you look to the left and 1 to the right. So you can have other types of neighbor configurations, and you can get really creative with that. And I've not done any of those, but I suspect that 3 and 1 above would probably yield some really cool patterns. So there's other neighbor configurations you can consider. You could change the rules each line, right? What if the rules changed on each row, right? Or what if rules change depending on something else, like some other condition or something like that? If there's a total of this many on cells in 1 row, then we change the rule for the next row. Or if there's only this specific number of off cells in a row, we change the rule for the next row, something like that. You could definitely improve the 5 neighbor rule set generator. As I said before, currently we're only able to see 1 million throughout that 4 billion space. What if you wrote some code that let you actually explore every single rule if you wanted to in that 4 billion size space? What if you didn't use a square grid? What if you used a triangular grid or a hexagonal grid? You could do all sorts of things. So whatever else you can imagine. So there's lots of different things you can further explore for this type of cellular automata. So I'm going to save this as 1D done, and I'll share this with you guys in the chat in case anyone got stuck trying to follow along with that. So that is the 1D portion of this workshop complete. We've got 1D, 2-state, 3 neighbor, and 1D, 2-state, 5 neighbors. So the file is in the chat in case anyone needs it. And that's the end of that first section. So I know we just kind of took a little break, but maybe we could have, I don't know, I don't need to go to the bathroom or whatever, but if you do, we could probably take a 5-minute break here, just because it's like a logical stopping point before we dive into the 2D and then the 3D. Oh, actually 2D, 2.5D, and then 3D. So if you need to go to the bathroom or get a drink of water, or if you have any questions or comments for me, we can take a little 5 minutes right now. So if anyone has any questions, let me know. And the thing about 5 neighbors, it's like, I have my favorite rules for the 3 neighbor one, but who can remember a 10-digit number like this? So I don't know any of my favorite rules for the 5 neighbor cellular automatas. But I just like to click this button and check out some new random ones. So this one's cool. You seem to get less of the like triangular formations in this. I'm not sure what the deal with that is, but they do still sometimes appear. And remember that these pink curves are one connected curve. So sometimes you get one where it's like all of it is one curve almost. Look at this one, that's crazy. All right, I am going to go to the bathroom. We will pick back up at like 1:18. No questions? Everybody's all set on this? It's good, I guess. 2D is a lot different than the 1D. Did you come up with a different logic to display the output curves? I'm just wondering if there's another way to create the joints of creating a mesh and then create the curves. Yeah, so Javier, that's a good question. There is. I mean, if you treat it like a graph, if you treat these squares like a graph where there are vertices and edges, what we're actually doing is following the graph edges at every less than 4 valence node, and then at 4 valence nodes we cross across it. So if I look here, if I was going to start here, I will pass this node. This one I will follow the edges around. This one I will pass. At this one, instead of turning right, I will just continue straight. And that's how this works, basically. So this is another 4 valence node, I'll pass through. This is another 4 valence node, I'll pass through. This is another 4 valence node, I'll pass through. This is another 4 valence node, I'll pass through. This is another 4 valence node, I'll pass through. Then I'll turn right. Then I'll cross through all this. Then I'll come down. Then I'll cross through all this. Then I'll come down, over. So it follows, you can actually code this to treat these edges as a graph and like traverse that graph by checking the valence of the nodes and then like what edges connected to that. But that's a little bit more complex than just using this mesh trick. I can't really remember exactly how I found that, but I had implemented this thing where I treated all these edges and nodes as a graph and then joined them in that way. And it worked exactly the same, but it was a lot slower. And so when I found this trick, basically, to doing it using meshes, I was very happy because it's a lot faster. It still takes a while, and I wish I could speed it up, but maybe that's something I'll address in the future. The slowest part of it is this line here, the polyline edges dot join equals join mesh dot get naked edges. I guess getting the naked edges, so the mesh like that, and turning them to a polyline array, pretty slow. But it's like the best way that I can do it right now. So if I were to dive in again on this problem, I would probably tackle it from the graph theory side and then try to optimize all that, because you could probably get it to be a little faster. But working with graphs in code is like kind of annoying. You have to have like adjacency matrices and like edge list and a node list, and then like, you know, you have to know which node is connected to what edges, all sorts of things. So it's a little bit more complex to code it that way. There probably is. I mean, there's probably another way too that I haven't thought of, but that's where it came from. I was working with it like a graph, and then I found this mesh trick to do the same thing, and I said, okay, that's a little bit nicer. All right. Okay, so this is all of our one-dimensional cellular automata. I'm going to disable all of it. We're going to jump into the 2D world. So just like with the 1D cellular automata, you want to be able to generate the rules like on the fly, like without having to type them every time. So we are going to create our own two-dimensional cellular automata rule generator. Oh, you know what? Actually, first, let me explain how two-dimensional cellular automata differs than one-dimensional cellular automata. Okay. So if I, yep, this is our one-dimensional cellular automata that we have. Right. So this is how one-dimensional cellular automata works. You create a grid, which we're calling just this first row, and then move that over time downwards. Okay. In 2D, you have a grid like this, and there's all these cells on it that are either on or off. And instead of just looking at each row, right, we're not just looking at this, we're looking at the whole grid at once. But for each cell, say for this cell, or this cell, or this cell, whatever, we are going to look at the 8 neighbors that surround it like this. So instead of just the row where you look at the left and right, we're going to look at all of these 8 neighbors that surround the cell. So this is how it's going to work in 2D. Okay, and the important thing is you don't count the cell itself. So it's not a 9 neighbor neighborhood. It is an 8 neighbor neighborhood because we don't count the current cell. So for this cell, we're checking all 8 neighbors around it in a 3x3 grid. And there's a different notation for the rules. We're not going to be using like the binary thing that we were doing before. Common way to create rules is this birth survive notation. So this is the game of life, the Conway's game of life, that famous cellular automata. Its rule notation its rule in the birth survive notation is B3 S23. That's not 23, that's S23, okay? So what this means, how you interpret these birth survive notation rules, is a cell that is currently dead becomes alive, aka is born, if it has exactly 3 neighbors. And a cell that is alive continues to survive if it has exactly 2 or 3 neighbors. And any cell other than that is either dies or stays dead. Okay? So looking at this one, right? We're going to be concerned with every cell, not just the on cells, right? Because some of these new cells could become alive in the next generation. And here's how that's going to look, okay? If we're following this B3S23 rule, the game of life, Conway's game of life, famous rule, this is what we call a glider. This is the things that move diagonally across the screen. So first generation, it looks like this. And then the next generation, following the B3S23 rule, we're going to have a little change here. So look at this cell, right? In the first generation, it is off. This cell right here, it's off. But if we look at its 8 neighbors around it, right? This neighbor, 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 we see that there are 3 that are on. This one, and this one. And that means it's going to get born. So this cell that is currently off here, in the next generation, it will be born. It becomes alive. It gets turned on in this generation here. And then this cell, it only has 1 neighbor. So in the next generation, this cell is going to be off. So it dies because it doesn't survive because 1 is not in the survival rules. So that's how that works. And over time, you can see how this cell glider moves diagonally. What's this? So it takes 5 steps for this shape to move diagonally 1 square, right? Or 1 unit. I don't know what you call that. And this repeats, obviously, because now we're back at the start here. And that's how this glider moves across the screen in this B3S23 rule, otherwise known as John Conway's Game of Life. It's important to note you can have up to 8 neighbors that can be alive around you. So the numbers go from 0 to 8, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8 is the max you can have. But you can also have something like this, where you are born if you have 2 neighbors and never survive. That's what this means. Since S has nothing after it, no cell survives from generation to generation. This rule is called seeds, I think, and I will explore it in a little bit. But basically, this means that if you have 2 neighbors, you become born, and if you have and no cell survives to the next generation. So there's always new cells instead of any cell lasting from generation to generation. It's really important to note that none is different than 0. Okay, and here's how this works. If this is a rule that has S0 in it, the next generation will look like this, because this cell is alive, but it has 0 alive neighbors, okay? And if it's S0, it will still be surviving. But if it was S none, this cell will die in the next generation. So none is different than 0 in this case. Basically, you can be born if you have 0 neighbors, but in this case, you survive, you never survive, because none of them survive from next generation to next generation. So these are like, you can have a rule that looks like B2/S or B0/S1456/7 or whatever. This rule would be like you're born if you have 0 neighbors, you survive if you have 1, 4, 6, or 7 neighbors. And otherwise, you die. That is like the assumed default, is that you die, essentially. Your cell that you're talking about dies. So that is just the basics of how we're going to look at 2-dimensional cellular automata with this BS notation, we call it, birth survive notation. It's the most common way. And in this way, if we use this notation, you can also look up online like cool and interesting rules that other people have already found, similar to how Game of Life is known and seed is known. You can have different named rules that people have made that exhibit cool behavior, things like that. Okay. Let me make a file here. All right. So we need to generate a rule generator. Oh, sorry, not perspective type. Okay. So just like how we have our rule generator for the 1-dimensional cellular automata, we're also going to have a rule generator for our 2D cellular automata. Okay. So we're going to have a C# script. Drag it down so we have some room between our 1D and our 2D. And just like how we had it with the 5-neighbor generator, I'm going to make it a button. So we're going to use button. So we're going to call that input step, make it item access, and we're going to change it to a Boolean type. Okay. And we know that we're going to be generating a list of numbers for those B values and those S values, those birth and survival values, right? So we're going to have two outputs. The first one is going to be B. Second one is going to be S. Okay, because we're going to output those lists from those outputs there. So I'm going to connect a panel to that one and a panel to this one. This way we can see what our B and S rules are. Let me give more room to Grasshopper, less room to Rhino. Okay, awesome. So diving into that C# component, zooming in on my screen. Make a component dot message equals 2D B/S. Okay. So how are we going to do this? Okay. If we know that our lists of possible rules for both birth and survival are 0, 1, 2, 3, 4, 5, 6, 7, or 8, there's actually one before 0 that I'm going to use a dash to represent none. You could have no cells that survive, right? So you can have none, 0, 1, 2, 3, 4, 5, 6, 7, or 8. Those are our list of potential rules that we can have for birth and survival, okay? So how are we going to make a subset of that list, right? Because I want to be able to create rules that are like 0, 5, 8, or like 2, 3, 4, 5, 7, 8, you know, skip 6 and 1. Or I want it to just be none, you know? So how do we create those lists of things for B and S? Well, what we're going to use is something called the Fisher-Yates shuffle. And this is like a way to shuffle a list in place so that we can reorder this thing. So now I could have, if I put in 0, 1, 2, 3, 4, 5, 6, 7, 8, I could get out like 8, 3, 4, 5, 6, 2, 1, you know what I mean? 7. So in a random order now, this thing has been reordered. That's what we're going to be using to do that. And then I will, once we have that, once we have this list here, after it's been shuffled, then I'll do something where I just take the first like X digits of it. So then I'll have like, you know, if I just take 4 digits, this list becomes 8, 3, 4, 5. And then that can be the birth rules. So this is how we're going to generate these lists in our rule generator here. And just to reiterate, none, which I'm representing with the dash, is different than 0. If I have S none, that means none ever survive from generation to generation. S0 means a cell survives if it has 0 neighbors. So those are different, just so you make sure you understand that. None is different than 0 in this case. Okay. So how are we going to do this? Well, first, we know we're going to use the Fisher-Yates shuffle, so let's make a function for that. Down here, I'm going to call this I'm going to label it Fisher-Yates shuffle. This is just like a known thing that people do, and you can implement this in any language. I use it a lot. It's very helpful to make this a function for you. Okay, so since it actually shuffles the array in place, it's not going to return anything. So it's not going to return an array. It's going to be a void, which is when you have a function that returns nothing because it acts on something. That's what it is. We're just going to call it shuffle. It's going to take in an integer array. I'm going to say R. Okay, that's what it's going to take in. Some room to write. We're going to start off, we're going to say int n equals r.length, so the length of the array. And while, we're going to have a little while loop in here, while n is greater than 1, we're going to do something. So while n is greater than 1, we're going to make an int called k, and that's going to be a random .next n minus minus. So we're subtracting 1 from n. So we're creating a number from 0 to n minus 1 every time. Don't worry, we will create this random in a second. Int t, another temporary value, is going to equal to our index n. And then rn equal to rk. And then rk is going to equal to t. So in this way, we are like picking a random value and then like shuffling it with another thing with this random, with this temporary placeholder integer t. So this allows us to shuffle this in place. I don't really want to explain the fishery shuffle too much. If you're curious about it, just Google it and you can learn. You can probably watch a nice little YouTube video on how the fishery gates shuffle works. But all we need to know is that if you put in an integer array like 0, 1, 2, 3, 4, 5, 6, 7, 8, you'll get something out that is those numbers in a different order. Well, not even get something out. It will shuffle them in place. Okay. And remember, we just used that random down there that we haven't defined yet. So let's make it here. Random rand equals new random. Random. And we know that we're also going to have, eventually, for the output, right, we need to have a list of numbers for our birth rules and a list of numbers for our survival rules. So let's make those now. List int b rules and list int s rules. Okay, so we just have those handy for later. All right. And we can be pretty sure that what we're going to output at the end, b equals b rules, and s equals s rules. Type. Okay, so we got some warnings here. Never been defined, whatever. That's fine. We're going to figure that out in a sec. Okay, give us some space to write our main stuff here. Remember, we have this Boolean button, so I'm going to wrap everything I'm going to write in this if step statement. I'll come down here and put that other thing, because everything we write is going to be, once I click the button, I want it to do all this. So that's why we're in that if step. Well, first things first, once I click the button, I want to make sure that the B rules and S rules are empty. So let's wipe the lists clean. Rules equals new list. S rules equals new list int. This is just so, after you click the button once, those lists have stuff in them. So when I click it again, the first thing I need to do is erase, wipe those lists clean. That way I don't just add more numbers to it. Then we're going to start with the full list of possible rules, besides the none. So what I mean by that is we're going to say int array b, we're going to create a new integer array b, equals new int array, oh man, interpolator, int array, and we're going to fill it with 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay? I'm going to copy this, paste it, S. Okay? Now we're going to shuffle rules. How are we going to do that? Well, shuffle B, shuffle S. So this is using the fishery gates shuffle we just created. It's going to rearrange all these numbers inside of these arrays. Okay, that's what we need. And now we need to truncate those, right? Like I said, how if you have these shuffled, then you take the first X digits, okay? And that's how we can create these random lists of numbers. So what we need to do is say int bn, like birth number or something, right, equals rand.next 0 to 10. And this is important, right? If you count these numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, there is 9 numbers there, okay? Including 0, that's 9 numbers. Ran.next gives you a random integer from 0, including 0, up to, but not including this maximum number. So if I just said 0 to 9, we will never get 9 as our number. So I want to be able to hit 9, so I have to put one more number. So this is going to generate a random number from 0 to 9, okay? A random integer, okay? So let me say this. This will make a random int from min up to and excluding max. So that's going to be min to max minus 1, okay? That's just so that you know how that works. And then we're going to say the same thing, int survival number equals ran.next 0 to 10, okay? Now we're going to use that to grab that many from the lists, okay? Grab that many from the lists, and that many being the birth number or survival number of the rules. Do a loop, int I equals 0, I is less than bn, I plus plus, b rules dot add b index I. So this is going to be grabbing, if bn equals like 4, right? We've shuffled b around, so these are in a random order. And then this will say, okay, just grab the first 4 numbers from that shuffled list and add them to the b rules, which is now an empty list, but we're adding them to it, okay? We're going to do copy paste and just do the same thing for s rules, sn, okay? So grab that many from the list. And that is all inside of the step if statement block for when I hit the button. And then this is unnecessary, but I like to do it sort the lists, just so that it's not like 8, 4, 3, 1. It'll be 1, 3, 4, 8, just so that's in order. So b rules dot sort. All right. Now, if you hit OK, you have to hit the button once, but if I give it room, you can see that we are generating random lists, and you can even get none. That's what the 0 is for. So, sorry, that's what the 0 is for here. So we can pick, sorry guys, I have to zoom in. You can pick no numbers from the birth list up to 9. Remember, it's max minus 1. But there is a little problem here, right? If birth number is none, you start off with certain amount of cells on from that initial grid. But if the birth number is none, that means that none will ever be born, which means that the next generation and every generation after it will be 0. Like there will be no alive cells. So we actually don't want the birth numbers to ever be 0. So we will change this to say 1, okay? This is important. We don't want none to ever be born. Otherwise, the cellular automata won't last more than 1 frame. You know, if you have none ever being born, you know, your cellular automata will quickly be very boring. Nothing will happen. Okay, so now we will always have at least 1 number in the birth rules thing. But it's okay if there's none in the survival rules thing, because we could have a rule where all cells that are currently alive die, but at least as long as new cells are being born, the cellular automata will continue to evolve over time. So that's just important. So this is our 2D birth survival rules generator. And when I click the button, I get new different rules here. Pretty cool. All right. I'm gonna copy this down 1 and this. All right. We obviously now need to make our main C# component, right? We have our rule generator. Now we need our actual main component. For that, drop in a C# script component, obviously. And we're going to have 1, 2, 3, 4, 5, 6, 7 inputs. 1, 2, 3, 4, 5, 6, 7. We're going to rename these. Capital B, capital S, capital X, capital Y. We're going to call this chance, just like how we had in that last one, right? You need to set the initial chance for cells for that initial frame to be on or off. Then we'll set this to seed, and we'll set this to reset. Okay. Now we need to assign what types of things these things are expecting, right? B should be a list access of type int. S should be a list access of type int, and you can connect those to there. That's nice. X should be a type int. Y should be a type int. Chance should be a type double. Seed should be a type int. Reset should be a type boolean. Now let's make a slider from 0 to 1. This will be our chance, or I might even call this initial chance, just so that's clear. This is like the initial frame. We start off with a grid randomly, like TV statics. Certain cells are on and off, and this is the chance for them. Just like how we have to start that initial row on the 1D one. Seed, just put in a number. You know how seeds work. That's good. Reset, button. That's good. And then X and Y. Let me actually move this up a little. That is our, size of the grid that we want, right? So I'll make it a number from 0 to 100. And this should be an integer. Okay. Now, make this capital X. Copy paste. Change that to capital Y. Good. Okay. So we've got our basics all set in here. One thing I do actually want to change right now is let's not use the rule generator for now, just because certain rules can be really unpredictable and I don't know what they all look like. So if I instead, just for debugging purposes, let's grab two number components. In the first one, set the number to 3. In the second one, set multiple numbers to 2 and 3, which if you remember, that is the birth and survival rules for John Conway's Game of Life. So I will group these and call this Game of Life. And I'm just doing this because there's known patterns and things that I will be able to recognize. So we know if our code is messed up or if it's working right, because I'll be able to see, those patterns are evolving the way that I would expect them to in John Conway's Game of Life. And once that's the case, then we can start using our cool rule generator to start exploring all sorts of different rules. Okay, so we've got an empty code thing here. Pull it up on my other monitor. All right, let's call this component message equals Game of Life. We'll change this to say, 2D cellular automata, but for right now, we are making it the Game of Life. Okay. Down in the custom additional code block, let's create our random rand, and we're going to have our grid, and that needs to be persistent. That's why we're putting it down here. So we're going to say data tree, and this time instead of integers, 0 and 1s, we're going to use true false values. So it's going to be a data tree of Boolean type. It's the same thing, but just slightly different. It's a little bit faster in the end. You'll see why, and I'll explain why when we get to that part. But for now, just know that we're using true false values instead of 1s and 0s. The same thing, though. This is going to be a new data tree type. And I know that it's almost taken 2.5 hours to make that 1D cellular automata. When I tell you that the 2D and 3D are faster to code, I can't explain why, but it seems more complex, but actually it's easier. So this is going to be we're going to get through these next two types of cellular automata a little bit faster, so don't worry, we're not running behind or anything. All right, so those are our data that we need to stay persistent, basically. But you know we have that reset button. So up here, we're going to say if reset, we want rand to equal a new random using the seed, okay? And we want the grid of Boolean, our data tree Boolean grid, to equal a function that we have yet to define, and it's going to be called initialize grid. That's going to take in our x dimension, capital X, our y dimension, capital Y, our random, and our chance, right? So this is just like how we set that first row in the 1D. We have to look at each cell, decide whether it is, you know, based on the chance percentage, it's going to be off or on. Same thing, but for the entire grid, you know, not just one row. And then we'll say A equals grid, just so that we know what's going on. Okay, so if I hit OK on this, hit the reset button, it's going to complain. It's going to say initialize grid does not exist in the current context, right? We're using a function we haven't defined yet. So obviously, we need to define that function. So I'm going to say, we know that it's going to be a Boolean data tree. That's the type of thing that we're going to return from this function. So it's going to be called initialize grid. And what we're going to take into that is our integer x for the row size, our integer y for the columns, our random rand, and our double chance. Okay. We know that since it's returning a Boolean data tree, we're going to need one of those to output. So let me just make that right now. Data tree bool. Grid, like grid, but with no I. I don't know, I just like to name it slightly different than the one that I'm, the real one, which is this right here. This is just inside the function, so I'm just going to call it grid equals new data tree. Oops, there it is. Bool. Okay. And at the end, we know we're going to be returning this grid. Okay, grid. But in the middle, what do we do? Okay. We need to, what does this function do? It's initialize grid with false or true, false or true values for each cell, depending on chance. Okay, so this is going to get our grid started, you know, that initial thing. And this is why it's really important for you to follow these capitalizations correctly. Because we're going to use, instead of I for the like enumerator for these for loops, we're going to use X and Y, just because that's easier to know like where we are in the data tree in 2D coordinates, basically. So we're going to say for int x, lowercase x, equals 0, x is less than big X. So this is like, you know, for each little x in the row, which is size x, big X, okay? X plus plus. And we're going to need to say, since we're addressing every item in every row, this is a 2D grid, so we're actually going to need a nested for, right? Int y equals 0. Y is less than big Y, which is the number of columns, y plus plus. We're going to say if rand.next double, this is just like how we started that initial row, is less than chance, add true. But remember, we need to identify where in the tree that is going, where in the data tree. We have to address this cell. So we got a comma. We say we're going to have a path, a GH path. So we're just going to say PTH. Okay. And then we'll say else. That same path. Okay. So where are we going to create this GH path? Well, for every row, we're going to create a new path. Okay. So GH path. GH equals new GH path X, okay? So for every row, there's going to be a new GH path that we address these cells to. Okay, now I hit OK. Are we complaining? No, it's working well. Let me just, for anyone watching the recording, here's the whole code. Pause the video now. But I don't want to look at this in panel form because this sucks. How am I going to know what this looks like? You know what I mean? But at least what we're seeing is a two-dimensional data tree where there's multiple true and false values in each list. What I want to do is visualize it on the Rhino side here. So much like before, this, we're going to take a square component, square grid component. We're going to actually add a new slider. I'm just going to make it like 0.125. And this is going to be the cell visual size. And this is literally just whatever size you want it to be. Since we're using a matrix of true and false values, there's no like actual rectangles or anything. So we can decide the size of them in the end through this. So we set that to size. We set extent x to the x. We set extent y to the y. See how these are connected to these. And then we're going to say, yeah, simplify this output because the data tree is unnecessarily complicated. And then we're going to get the area of each of these cells just to get this point in the center of the cells. You can get like the points on the corners, but it's just easier to do it this way, I think. Plus, this won't need to calculate more than one time. Like on every iteration, this doesn't recalculate. So don't worry if you have like a huge grid and this takes a while, only do it one time. Then we're going to use a dispatch pattern. And the list is going to be these centroids, and the output is going to be the dispatch pattern. And now if I do a little geo, and I hide all this, let me put my Rhino window back to normal sized. Come on, there we go. You can see we've got a random scattering of things. And if I hit seed and change it, we're dispatching these points in a random fashion. And if I change the initial chance to be lower, we're going to have less and less. And if I change it higher, we're going to have more and more. Okay, that's cool. But why did I do it this way? Well, because we can use what's called the symbol display. So let's grab the symbol advanced component and the symbol display component. The location is going to be plugged into the dispatch output A. We're going to flatten that output actually also. On the symbol advanced, we're going to plug that into the symbol display output. We've got these weird lime green like arrow things. It's not what I want at all. So if you right click the style input of the symbol advanced, change it to square closed. That looks okay, but not exactly how I want it. What we're going to do now is going to make some adjustments to this. Set width to 10 and adjust to true. So width to choose 10, adjust, set that to true. So that's looking horrible. Don't worry though, we're going to fix that in just a sec. The cell visual size slider that we made, we're going to connect that to the size primary and the size secondary. Now we've got this nice little grid of squares here. And this is the reason I'm doing it this way. Is just this is a lot faster than making like boundary surfaces and then coloring them, or like mesh faces and then coloring them. This is just like even faster because the symbols aren't real geometry. It's just like a thing that we can visualize for graphics only. I'll get a swatch. I'll change it to black. I'll plug that into the fill and edge. Nice. Now we've got this. That's looking really good. I'll set this to 0.5. And now you can see we've got our initial grid here. So when we change the seed, we hit the reset button. We can mess with the initial chance to get less. to get more. I'll keep it at 25, so there's an even chance for a cell to be on or off. And this is our initial grid that we're going to start our 2D cellular automata off with. I'm going to just clean up how my components are laid out. I like to have a nice clean thing. Okay, so this is our like initial grid for the cell states that we need. All right. And then basically there's like one step to creating this working thing, which is pretty crazy. It's not even that much harder than what we've already written. Okay, I'm gonna copy and disable that. The reset button. Okay, so I'm gonna make it just a 30 by 30 grid. I don't know why. There's no reason. You can make it whatever. There's our nice little initial frame. Let me just make sure everything looks good. Okay, so now we need to implement the main function, right? How do we do that? Well, I want it to look like this, okay? We're going to say create the next grid using the current grid. It should be giving you deja vu. It's like exactly the same way we created the next row using the current row. Except this time we're concerned with the entire grid at once, okay? What I want this to look like is this. I want it to be grid equals generate, taking the birth rules, taking the survival rules, and the current grid, okay? I want it to be in that format. And we're going to be using a timer component, which they've changed the name of that to trigger in Rhino 7. I don't know why. Pretty sure it was called timer. This is what we're going to be plugging in to this. So every time the timer triggers the C# component, it's going to run this line of code and then output it. Okay, and that's why we have this in a if block, so we can reset it and restart the simulation. So we're going to let it run over time. So every time it runs, it's going to execute this line of code and this line of code. Okay. All right, we've got the initialized grid done. So let me copy this little barrier, paste it down there, so we have some room to write our main function. So this is going to be the main function. We know it's going to be a data tree of booleans, and it's going to be called generate. So let's just pop that all in there. Public data tree bool generate. It's going to take in a list of integers b, that's the birth rules. It's going to take in a list of integers s, that's the survival rules, and it's going to take in the current boolean data tree of grid called grid. Okay. And what is this function? How's it going to work? Right. This is the main function. It takes in the b/s rules and the current grid, outputs a new grid. It's going to look at each cell in the grid and its 8 neighbors. When I say its, I'm talking about the current cell that you're looking at. So for each cell, that cell is going to look at its 8 neighbors. And creates the next state of that cell depending on S rules. Okay, so pretty similar to the 1D, except now we're looking at more neighbors in a different way, and we're updating the entire grid at once instead of just rows. Okay. All right. Well, we know that what we're going to output in the end is a temporary, it's a grid, right? Well, first off, we're going to be referencing the amount of rows and columns in this grid a lot. So for ease of use, let's assign those to a variable. Okay. int columns equals grid.branch count. And int rows equals grid.branch 0.count. So this is, the number of columns, and this is the number of rows. And now instead of having to type this every time, I can just type rows, because we're going to be using that a few times. Okay, so we know that we want to output a Boolean data tree, right? And obviously we have the original one being passed into this function. And so we're going to need like a temporary one to work on to create that next generation of the grid. So we create temp grid. But first, initialize with all false values. I guess I shouldn't put that in quotes. First, we initialize it with all false values, okay? And we do this because cells by default are assumed dead if not born or surviving. Right? That's why there's only birth and survive rules and not any dead rules. If it's not birthed or surviving, it's dying. So we assume that all cells by default are dead or false, we call it, right? So that temp grid, okay? Data tree Boolean grid, why not? It's perfect. Equals new data tree rule. Okay. And we have to fill it with all false values, okay? So how are we going to do that? We're going to make a double loop, just like we did for the initializing. So for int x equals 0, x is less than columns x plus plus. Then we're going to have another one here, int y equals 0, y is less than rows, y plus plus. And just like before also, we're going to take this line, ghpath path equals new ghpath at index x. Okay, that's going right in there. Oops, I put that in the wrong spot. Sorry, guys. That should be here. Let me give a little space so you can see what we're doing. We should have the x for loop, and then create a new ghpath, and then the inner y for loop. Okay, that's how this should look. And then we just say temp grid dot add false to that ghpath. Okay. So this is now a temporary grid, and it's all full of false values. Every cell is false in this grid. What we'll be doing now is looking at each cell in the real grid and then assigning that new state to this temp grid before we output it. Okay, so some space because now we're about to write some code here. We're going to have the main loop where we look at every cell and its states. So you can imagine now what we're going to have is a two-dimensional loop, right? A nested for loops where we loop over all x and all y, so out every column and every row. Then we're going to have a smaller loop also, where for every one of those cells, we have to look at all of its neighbors in a smaller loop there. But there's only 8, so that's not too much nesting. So another for loop for int x equals 0, x is less than columns, x plus plus. For int y equals 0, y is less than rows, y plus plus. And push those all the way down because everything we're going to be doing is inside this double nested loop here. Okay. What's the main thing that we're doing here, right? We're going to look at every cell and its neighbors, so we're going to need to count the neighbors. And if they match up with one of those birth numbers or the survival numbers, that's how we know. So we need to keep track of the amount of alive neighbors for each cell that we're looking at. So, counting the neighbors. We're going to have a little block of code here. And this is to keep track of the true And true, I just mean instead of false, right? So the on neighbors, not the off neighbors, the alive neighbors, not the dead neighbors, the true neighbors, not the false neighbors. Create an integer called neighbor count and set it to 0. And now we're going to count all the true neighbors in a 3x3 grid, and we're going to, including wraparound through modulo magic, I'm going to call it. So just like how when we got to the end of the first row, we had to wrap around and look at that first cell to get that left neighbor or whatever it was, you know? When you're at that first cell, your left neighbor is the one all the way at the right end, you know? So same thing for this. Just hit this here. Come back. Don't do this. This is just so I can show you what I'm saying. If we're looking at this cell here, its right neighbor is this cell here, okay? You know what I mean? And if you're this cell here, your bottom neighbor is this cell here. So we have to do the wraparound in 2D now. But it's not that hard. Jump back into this. Zoom back in. So we're going to include the wraparound through modulo magic. So we're going to have another mini for loop inside here where we can look at the 3x3 grid of cells around our current cell. So we're going to say for int I equals -1. This is so important. For int I equals -1, I is less than or equal to 1 I plus plus. If you don't type that right, it's going to really mess up. So make sure you start your for loop here at -1 and end it less than or equal to 1. Basically, this means if we have our current cell, we're going to look behind it 1, at itself, and 1 to the right. But this is working in 2 dimensions, so it's not just only to the right and left, it's also above and below, and then also the diagonals. So for int j equals -1, j is less than or equal to 1, j plus plus. This is just our mini loop where we're looking at a 3x3 grid here. And now we're going to say neighbor count plus equals, and what are we looking at here, right? We're going to be looking at every cell around our current cell, those 8 neighbors, and we're going to be checking whether their values are true or false. And we're going to convert those true or false values to 0 or 1 so that we can add it to the neighbor count integer. So if a cell is false, that number is going to get converted to 0. So it doesn't matter. If that's a dead cell, it's not going to be added. If it's alive, if its value is true, we're going to convert that to 1. We're going to add that up. So this will now become 1, right? So the way we do that is we have to say convert.toInt32. And this can take in a Boolean value. Okay, I'm just going to keep it empty for now, just so you can understand what's going on there. Inside of those parentheses, what we're going to say is we need to get the cell that we need to look at, right? So this might get a little confusing without a visual aid, so let me just draw one real quick. Okay. Right. Oh, how ugly. Hang on. Okay, there we go. So if we're looking at this cell, right? This open. Smaller. Okay, great. If we're looking at this cell, we need to get the index of this cell here, this cell here, this cell here, this cell here, this cell, this cell, this cell, this cell. And then we're doing that through this for loop. So this is going to maybe be a little confusing, but hopefully you get it. We're going to look in the regular grid. So we're going to say grid, zoom in a little bit more, grid.branch, open parentheses, and include that. I'm going to say we'll add the convert.to and 32 later, just because there's so many parentheses and stuff. I don't want you to get confused about it. So we're going to say grid.branch, two parentheses, x plus I plus columns, close parentheses, modulo columns, close parentheses, open bracket, open parentheses, y plus j plus rows. Now I need to scroll over. Y plus j plus rows, close parentheses, modulo rows, close bracket. Okay, so what this is saying is, if you're on the edge of the grid, right, this is just how we're going to wrap around back to the end there. So X is the current cell position in the grid. I is the left and right cells in this inner for loop, and then columns is the number. So if we are like at the very edge and I pushes us over that, it will wrap us around to the left side. And the same thing goes for the rows. And now what we can do is convert .to int 32 and wrap all of that in a set of parentheses and add your semicolon. And that's just because this returns a true or false value, and this will now convert that to a 0 or a 1. That way we can add it to the neighbor count, which is an integer, obviously. Okay. So do you see the problem with this? We're looking at this cell, then this cell, then this cell, then this cell, then this cell, this cell, this cell, this cell. But we don't want to include the current cell's value. We don't want it. We only want the 8 around it, not all 9 in this three-by-three grid, which is what we've now added up. So what we actually have to do is subtract the current cell's value since it was included in the above neighbor checking loop. Subtract the current cell's value since it was included in the above neighbor checking loop. Okay. So all we have to do is say neighbor count minus equals convert .to int 32 grid .branch x y. So that's the current cell's value as a true or false value. We convert it to an integer and we minus it from that neighbor count total, which we added up. So this is how we correct for covering that in the neighbor checking loop. We just subtract it after the fact. It would just be more annoying to write this without that, you know. I mean, we could have like an if statement, if I and j both equal 0, skip it, but whatever. This works the same. Okay, so now what we've got is we've got a loop where we're looking at every cell. We've got at each cell, we got a little loop here where we add up the states of all the cells surrounding it. We hold that total in this neighbor count. Okay, and remember that that's important. That's what the you know, if you have 3 neighbors, then you live, or if you have 2 neighbors, then you die. Like that's how we keep track of that. This is the neighbor count that we compare to this. So what we do next is we have to check the neighbor count against the BS rules to decide the fate of the current cell. Okay. Or you could probably more accurately say to create the state in the next generation or whatever, but I'll just leave it. First things first, see if the current cell is false or true, if it's on or off, right? Off or on, whatever. So we're going to have like a whole bunch of if else statements here where we have to like make a decision based on those values. So if grid.branch x y equals false. So first we'll check if it's a dead cell. Let me just label this. Cell is off. Okay. So if current cell is dead, This might look a little confusing what I'm about to write, but just trust me that this is how it should be done logically. If v.count is not equal to 0, this is basically saying if there are no birth rules, none are ever born. Okay. So as long as there's one birth rule, right? Then we move into this next section here. We're going to loop through the birth rules to check if the neighbor count equals any of those birth rules, right? So for int I equals 0, I is less than b.count, because we're looping through every one of the birth rules, I plus plus. Got a comment there, loop through the birth rules. So for every birth rule, if neighbor count equals that birth rule, if the neighbor count is equal to any birth rule, temp grid dot branch x y equals true, because if the neighbor count is equal to a birth rule, the cell gets born. Cell is born. Hooray. And then what we can actually also do is say break, stop looping through birth rules, move on to next cell. Okay, so break will break us out of this loop because we don't need to check anymore because the cell has already been born because it matched one of the birth rules. Okay, then we exit out of that, we exit out of that, we exit out of that. 1, 2, 3, 4. Okay, so if the cell is on, that's where we're at now, right? Else, and that else is the opposite of this. So if the cell is off, we do this. Otherwise, the cell is on. Cell is on. Okay. We're going to do pretty much the same thing, right? If the cell is on, we first have to check if there are no survival rules. So if s.count equals 0, temp grid dot branch x y equals false. So if there are no survival rules, the cell must die. So if there's no survival rules, every cell is going to die every time. So if it's on, it's going to be killed. But if there are survival rules, else, now we're going to loop through the survival rules to check the neighbor count against it, just like how we did for the birth count. So for int I equals 0, I is less than s dot count, I plus plus. Survival rules. We check if the neighbor count is equal to it. If count equals s index I. So if the neighbor count is equal to any survival rule, temp grid dot branch x y equals true. And that means the cell continues living. And stop looping. Cell. And then we can close out all of that. So we've got so many nested things, but this is probably the most efficient way you could do it. I mean, there's other ways you could do it, but you'd have to check a lot of conditions on every loop. So this way you kind of avoid checking unnecessary conditions when you don't have to, which would slow things down a little bit. Okay, and then close out almost all of these, leave one and say return temp grid. Oops, return temp grid. All right, so going to zoom out just a little bit so you can see more of the code at once. So just to make sure everyone sees where the brackets end, right? The whole function ends here. Right before that, we're returning that grid. This is the closeout of the main loop. This is the closeout of that inner main loop. And then this is for the cell being on, and et cetera, et cetera. So if I hit OK, oh, what do we have? Oh, let me X out of that. If we're running the game of life right now. Maybe I'll make this 50 by 50, just so we can get started looking at it larger. All right, I'm going to hit run. Wow, what do we have here? So I'm looking out for something like this, because that tells me that we've implemented it correctly. These things that repeat and just move, they're like 3 bars. I'm also hoping to see a glider at some point, because that'll really confirm it for me, because those gliders take a specific form. Okay, so we've reached an end here. Let me hit a different seed. I want to see a glider. Come on, gliders. Where you at? There's one. Nice. So there's one that hit and exploded. So I'm very confident that we have just implemented Conway's Game of Life in Grasshopper. Very cool. Very fun to watch go. And the reason that we chose to do a Boolean grid is because the output goes to the dispatch pattern. And if you do integers, this dispatch pattern has to do a little bit extra computation to cast those Booleans as, those integers as Booleans. And it makes this a little bit slower. And that's something that it has to do every frame. So there's no reason to make it an integer grid. If you make it a bool grid, you skip that. So this is how that works. And we can make this way bigger and see what's going on. We got our little life. And you can see already it's, if this had to take longer at each time, this would be a lot slower. This stuff only calculates one time. This and this are both going every frame. Pretty cool. Okay, so we've got Conway's Game of Life going. And that's really nice. I'm going to hit save. I'm going to copy all of this down one, because now we're going to, if a glider hits a side, will it come out from the other side? Absolutely it will. Hang on, let's see. Here's something that we can do. I will set the initial chance to be like lower, so less start. So maybe we'll have more open. Let's see if we can see a glider come around on one side. Not many gliders right now. We'll get one. I'm sure there's one right here, but it's going to hit. Come on. Well, if we don't see one, just trust me that they do come around from the other side. If it comes in at the top and then goes diagonally down here, it'll come out over here and continue diagonally down that way. It's pretty cool. So Conway's Game of Life is probably the most popular one because you get all these different patterns and they seem to persist for a long time. They maybe almost die out and then they suddenly really rise in chaos and last for a lot longer. Oh, look, here comes one. It's going to come out over here. There it is. Nice. So we just saw it happen. Okay. But anyways, I'm moving on to the next section. I just copy and pasted all of that because now what I want to do is add, well, first, why don't we try it with some of the generated rules, okay? Instead of Conway's Game of Life, let's forget Conway's Game of Life for now. Let's try it with some of our own random rules, why don't we? Enable that, that. A lot of them are going to be pretty bad, I'll tell you. But you definitely can find ones that are cool. Like, oh, look at this. This is like a, I don't know. Oh, what's going on there? Very interesting. And maybe if you start with like a lot less, you see some more interesting behavior or something. If I do like 0.01. Oh, what was that? At first? I don't know. Very interesting. So, oh, that one was cool. Look at this. So you get a ton of different behavior. So this one is like spreading out from this one thing, and cells that become alive stay alive, it seems, most of them. So you get a ton of different variety of rules in these things. One thing that you should definitely check out, back to the internet here, if you search lifelike cellular automata, there's a wiki called conwaylife.com. Link in the chat. This is a list of lifelike cellular automata, and you can see that the rule strings are in the format that we expect, B3S1234, right? So here's a really cool one, B3S12345. That one's called maze. So these are like named rules, which is cool. So actually, let me unplug our rule generator and get some num components. So it was B3, so we'll just put 3 in 1, and that will go into B. We've got another num component. And this was S12345. 1, 2, 3, 4, 5. Come on. If I plug that in and hit this, well, maybe I need a new seed, or this is just not enough. 0.02. Look at this. This creates a maze-like form as it spreads throughout. So you can see where it gets its name from. You know, the maze rule. This one's really cool. I really like this. That website is great. You can see all sorts of different rules there. Oh, you know what? We should definitely look at the seed rule. So that's the maze rule. Very cool. I really like that one. But you see this one, seeds. This is the one I was talking about when we were first talking about it. It's B2S. So there's no cells that survive. It's an exploding rule in which every cell dies in every generation. Okay? So let's check that out. So that's B2. And then S is none. So let's check it out. So if I pause it, and I could go 1 frame, none of the cells that are alive in the next frame. So this one quickly explodes and becomes chaos, but you can see in the beginning how it's pretty cool. So this is the seeds rule. So this is an example of how you have none, right? Different than 0. So this is the seeds rule. So you can get a ton of cool rules from this website here. And even look, Conway's Life is here. B3S23. Some really cool ones. Here's one that I really like. It's called Vote. B5678. Set that. 5678. And S45678. 45678. And it almost looks like nothing's happening, right? But that's because this rule really requires a lot more cells in the beginning. And this one's really cool. It basically conglomerates into these like smooth regions. I know that people who play like D&D or like are creating their own like dungeon crawler 2D things use this cellular automata to generate like caves, like a map of like a cave, because you can use this for like, you know, some video game you're making. You can use this cellular automata. All you have to do is start with random, and then it will smooth out and then stay stable, and then you can say, okay, that looks good. It's like a little cave now. You have all these spaces to walk around in different rooms and things, so pretty cool. One thing you might have noticed is when I hit the button, it's not exactly that first frame. It's like the second frame on the reset, and that's just like an issue with either the C# component or the button in Grasshopper. It like triggers twice, so we don't get to see that initial frame, unfortunately. Kind of a bummer, but it just is what it is. There is like a way to get around that, but I'm not going to dive into that. You have to like, I don't like it. Okay, I'm not sure if I explained that well. It's nothing you need to worry about. So anyways, that's a pretty cool rule. That one's called Vote. Anyways, plug in a random thing here. One thing that we probably want to try to do is come up with different ways we can start the automata off, right? I don't want it to always start off fully random, like even if I have it less. Like I don't want it to be like this. Like what if I want to start with 1 cell in the dead center? Because then I can see like nice symmetrical patterns emerge. So how are we going to do that? Well, we're going to add another thing here, another input, and we're going to call that mode. And this is just that starting. We could maybe call it like starting mode or something, but I don't want to type that much. I'll set that to an int. So mode is set to an int, and we'll set this to, we'll have a slider where you can have two modes, right? Where it's all over random, like it is now, and 1. So 0 is all over random, and 1 will be one single cell in the center. So we have two ways to start this cellular automata off. Initial mode. Okay, plug that in there. And this is actually quite easy to add that functionality to it. Not too much code. If I hop into there and I'm in the initialize grid function that we've created, all I have to do is wrap this and say if initial mode, if mode equals 0, do this. Else, if mode equals 1, we'll do something else, right? Obviously, now I need to pass in mode. Sorry, that should be int mode. And up here, I'm going to add mode as well. Okay. So now we can pass in that mode variable. And here we go. I'm just going to copy all of this because we don't want to have to write those double for loops again. Okay, path x, blah, 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 blah. And instead of this line here, if ran next double is less than chance, what we're going to have is a condition that only is true for that centered cell. Okay, so what we're going to say is if x, zoom in a little bit more for you guys, if x is greater than or equal to math.floor of big X, the number of rows, right, divided by 2.0, and X is less than or equal to math.floor, same thing, X divided by 2.0, and we're going to do the same thing for the Y's, okay, so let me just copy all those. If y is greater than or equal to the number of columns, aka y, right, big Y, and y is less than that, and this is kind of a tricky line because there's so many different capitalizations. So actually, let me just put that in the chat, okay? I don't want you guys to write this wrong. It's kind of annoying to write that one. Basically, this is going to say it's going to get only this condition will only evaluate to true for the centered cell in the grid. Okay, and we can see what this looks like. So initial mode is like this, but if I change initial mode to 1, now it's just that one cell in the center, and it's not going to work for every rule, right? Because most rules, it will only work for rules that have a 1 in the birth rule list. So if it has more than that, this cell doesn't have 3 neighbors, which is what the current rule is telling us. It needs 3 neighbors. So we can, there we go. Nice. Very cool. So you can get some really nice symmetrical things. So you see this birth rule is 1, 3, 4, 5, 7. So because it has a 1, this initial cell can survive to the next generation. And we get these nice symmetrical things. It won't be perfectly symmetrical if your grid is an even number. See, this is 100 and 100. And you can see that this corner in the bottom left is different than the corner in the bottom right, and so if I change these to say 99, then we can have a perfectly centered cell in the middle. So just so you know, this will now be perfectly symmetrical on all corners and sides. You can see it looks exactly the same on all corners. So you can get a very cool symmetrical looking outputs. They look like mandalas or like rugs or something, or I don't know, some crazy kind of visual thing. Very cool. So that is the 2D cellular automata. And now you can explore different rules. One thing I do want to note, I don't know if you have epilepsy or something, a lot of these rules, if you have none that survive, they flash really heavily. Whoa, this one was cool. Who's that one? It's some crazy ones. A lot of them like flash really heavily. Like, let me try to find one that does. Yeah, like this one. So if you have like epilepsy, I don't know, be careful. I guess I need to give like a flashing visuals warning. And that's because none survive, right? But then you do get born if you have 0 neighbors. So all of these ones out here have 0 neighbors, and they don't survive to the next one, so they are constantly turning off and then turning back on, turning off and turning back on. So you get like a huge amount of like flashing. It can be kind of headache inducing. So just keep that in mind. If you don't want that, you could write some sort of thing inside your rule generator to say like, okay, never let none survive while there is a birth rule of 0, because then you won't get that flashing, basically. All right, so that is the 2D CA. Oh, you know what? We can change this from the game of life to 2D CA, because we're not just using the game of life. Now we're using, any birth rules that we want. And you get some really cool, rug-looking things, I guess. But yeah, that's pretty cool and all. But what if I wanted to see that in 3D, like over time, right? What if I wanted to move upwards, like game of life, 3D Grasshopper? I'm sure if I Google this, we're going to see some incorrect labeled things. Yeah, game of life, 3D. No, wrong. This is a 2.5D version of the game of life. It's not 3D. People really love to say this is a 3D cellular automata. It's not. This is a 2.5D cellular automata. This is the game of life over time, moving upwards. So we want to do that too, right? I want to see that. So I'm going to copy this, move it down, disable my old one. And what we're going to add is another output to our main 2D cellular automata. We're going to call that iterations. My code. We're going to dive in, and we're going to add underneath in the persistent data section here, we're going to say int its, its, short for iterations, right? On the reset, we want its to be set to 0. And every time we update the grid, we want its plus plus. And then we'll say iterations equals its, so that we can output it. Okay. Now you can see if I put a panel, and I run this, you can see that it keeps track of the number of generations we've created. And when I hit reset, it resets. So in this way, we can now let me print this just while I'm working on it. We can now get a multiplication component. We're going to multiply the cell visual size by the iterations. And we're going to take a unit Z component vector, plug that into the result. We're going to take a move component, plug this into the points being dispatched output, and you can see that, and set it to this. And so you can see what this looks like. Let me close this. And you can see it's moving upwards in space. And that's perfect. That's what we're going to want. Except now I want a data recorder component on this. And what are we going to see here when I run this? Let me press reset and run it. And I'll pause it. That's enough. Got a lot of points there. It's looking pretty cool. But I want to see it with some geometry, right? Obviously. So let me make a center box. I'm going to get a division component and divide by 2. And what's going to be divided by 2 is that cell visual size. We're going to plug that into the X, Y, and Z. So you get this little box. Then we're going to get the simple mesh component. This isn't from a plugin, I hope. Then we're going to get the move to point from Pufferfish, I think. And this like literally might be the only thing we use Pufferfish for. And you could honestly do this with like just 2 components instead of 1 right now. We're going to move that from the origin to these points. Whoa, let's see. Step up. This will be like our visualization of the 2.5D cellular automata. Okay, let's see if I get a custom preview. And I'll do a swatch. I'll make it white. Looks good. And I'll change this to the rendered mode so you can see it. Oh, very cool. It is upside down, but that's okay. I see some people asking for the most recent GH in the chat, so let me save as 2.5D done.gh. Grab that for you guys. Off the chat. There it is. Okay, sent. So here we have that. So now you can see we can get these like really cool structures built. It is upside down. I mean, in my opinion, I guess technically it's really not upside down, but whatever. One thing that's really cool is to plug in once again the game of life. Bring that down here. Come on. I'll move this out of the way. I'm going to plug in the game of life. And we'll start with regular initial start. Let me clear the data recorder, obviously. I don't think I want it to be 99 by 99. I'll make it like 50 by 50, something like that. And now you can see what everyone on YouTube calls 3D game of life. It's clearly just the 2D game of life moved upwards over time, not a 3D cellular automata at all. It's just the 2D one moved upwards over time. We get these like very cool, you know, like towers and formations and things. So it is really cool. So I see why a lot of people make tutorials for doing it. But we've done it better because now we have, you know, we can make any rule we want, not just hard-coded the game of life in there. That's just an option for us. And we can see it over time. Like, you know, what's a really cool rule is that maze rule over time. So that was 3, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The maze rule that we had. That one's like really awesome looking over time. Ready? Ooh, look at that. Pretty cool. Maybe if I set the initial chance lower, kind of better. Oh. Oh, come on. I'm going to move this seat around until I get one. Fine. Okay, here we go. Yeah, now we're talking. Look at that. So just be careful when you're doing this because it does get pretty heavy. Alternatively, because this type of thing gets really slow when you have a ton of data, you could just use Dendro to like voxelize the points, but it's not pixel, like it's not like voxels like this, like it's smooth. I'll show you that. If you go to Dendro and you take convert points to volume, you take these points, point radius of, I guess, I don't know, 1. We got to get the create settings component, settings, and then you do volume to mesh. Radius must be at least 33% larger than voxel size. Okay, set voxel size to 5. Oh, maybe that's too much. Point radius should be cell visual size. Voxel size should be. Yeah, now we're talking. And then volume to mesh, volume settings. Maybe hide this. And this is just like another way to visualize. And sometimes I think it's faster, but it is like obviously more blobby, than the just moving cubes into position through the center box method. But looks pretty cool. So that's just another way to visualize it, but I think I prefer this because it's just like more rigid. If you really wanted to get crazy with it, you could use the voxel mesh component, and that's from Pufferfish. But this definitely gets really slow when you have a lot of points. Like 25,000 points will probably take like 5 minutes or something, at least on my computer. But I found that this is faster than like this component, which is from Ngon by Petros Sartos, I think. So good job, Mike, on this component. It's the fastest one I've found for voxelizing points into a solid closed mesh. I do use it, but I'm not going to use it during this because it takes like 5 minutes. And don't forget to clear your data recorder when you are done with it. I'll group that, and I'll say this is visualizing 2.5D. And then I'll group all of this, and I'll say 2.5D CA. So now we've got our 2D CA and our 2.5D. The only difference is the iterations output. So I mean, you can just use this as the 2D CA and then just not use the iterations output to move things over time and whatever, that's fine. So that concludes our 2D CA, 2D and 2.5D. Yeah, it's built off Mateus's code, yeah. It's really nice though, it's fast. That's the one I used. I mean, it's the fastest. It's still slow, but it's the fastest. Okay, so what else could you do with this? Panel going, we'll talk about some further exploration you could do, right? Exploration. Well, you can have different neighborhood types. Okay. So the one that we're looking at right now is all 8 around that cell in a little grid, right? But you could have, and that's technically called the Moore neighborhood, M-O-R-E. You could have the von Neumann neighborhood. And the difference between those, just quickly explain. Right? So if you have this cell in the middle, the Moore neighborhood is all 8 of these cells, okay? The von Neumann neighborhood is just the cells on the face, none of the diagonals. So that's a different neighborhood type that you could use instead. And you can see what sort of patterns you get from that. You get all sorts of different rules and things too. So you can have lots of different types of things. Or what if you just looked at only the diagonals? You could have all types of different things. What if you looked at, like 2 layers? I'm not going to draw it all, but you know what I mean? If you had another layer of cells outside, you looked at 2 deep Moore neighborhood. So you could have Moore or von Neumann, you could have expanded neighborhoods, which is what I was just explaining there. You could have cross-shaped neighborhood, you could have diagonals only neighborhood, you could have alternating neighborhoods. So maybe on even frames, you check the Moore neighborhood, and on odd frames, iterations, you check the Moore neighborhood, or I mean the von Neumann, whatever. You alternate between those. You could have You could use circles as your neighborhood. So like, if you try to draw a circle, like a Minecraft circle, like these. These could be your neighborhoods, okay? Oh, come on. So your neighborhoods could look like this instead. You could have like way crazier ones. You could have multiple circles. You could have multiple neighborhoods, yeah, and have them overlap and then like somehow adjust. You could have more than 2 states. You could have 3 states, 4 states, 10 states, 100. You could have directional rules, right? So I just did this, but currently it doesn't matter if this cell is on or this cell is on or this cell is on. It's only going to be counted as one cell. So it just counts up the total number of alive neighbors. But what if it mattered whether it was this cell or this cell or this cell that were on? You could have a directional rule, and that allows you to have so much more variety of the thing. So currently what we're doing, this is technically called a totalistic cellular automata because it's only concerned with the total number of neighbors. You could have directional cellular automata. You could do rock, paper, scissors cellular automata, which is a cyclic automata. You could do a forest fire / a predator prey type automata, where like certain cells attack other cells, like in a way. You look these up, you'll see. You could move on to abelian sand piles, which is another type of 2-dimensional cellular automata, but works a lot differently than what we've done here. You can even try to come up with some other rule scheme besides birth survive. I don't know what that would look like, but you can come up with it. You could definitely do this on non-square grids. Triangle, hexagonal, irregular. What if you did this on a Voronoi grid? That would be really crazy. What kind of rules would allow patterns to not just instantly die out on a Voronoi grid? How would you get the neighbor counts on a Voronoi grid? That would be really tough, but could be really cool looking. What else? Can't imagine. So there's lots of different things you can explore with this. All right, it looks like we've got about an hour 5 minutes left. And that's actually fine because the 3D doesn't really take very long at all. So we're going to dive right into that right now. I'm going to just highlight all this, disable it. Okay. All right, so for the 3D, we're actually going to grab our rule generator for 2D BS rules generator. And we're just going to drag this down because we're going to modify this for the 3D. X out of here. Oh, let me just show you. Yes, one more time. We'll jump into my explainer document here, and I'll show you 3D. So in 2D, you have 8 neighbors. In 3D, you have 26 neighbors, right? So if you look at this, you can see that like little orange cell in the center, this one that I have highlighted. You're looking at all of these cells around it. So in a 3 by 3 by 3 grid, minus the current cell. So instead of 27, which is 9 times 3, you have 26 neighbors. So you're looking in a 3 by 3 by 3 grid. But you could do, those different types of neighborhood types in 3D also. So, but we're going to look at the standard Moore neighborhood in 3D, which is 26 neighbors, 1 layer away from our cell. Okay, so we've got our 2D rule generator here. What I'm going to do is edit this to be our 3D rules generator. It's quite easy to edit. It's not much different. One thing I will note is that instead of having 0, 1, 2, 3, 4, 5, 6, 7, 8, you also have 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Those are the possible ones. I don't want to type that again. So let's just change how this works, why don't we? I'm going to make this a int of size 27 array. Copy that. S equals a new int of size 27 array. And then I'm just going to make a loop to fill them both. So type all those numbers. So I is less than 27, I plus plus. And remember, it's 27 because 0 is included. So you get 0 to 26 is 27 different possible rows. So plus, and then B, I equals I, S, I equals I. I just don't want to type all those numbers every time. Then all we need to change now is we generate a random number from 1 to 28 for the birth and from 0 to 28 for the survivals. And that's literally the only difference. So now we can generate much larger lists for our birth and survival rules. Come on. Let's see. Yeah, look at that. Because you can have way more numbers. So, sorry, I was doing way out. Yeah, you can have way more numbers. So that's the only difference between the 2D rule generator and the 3D rule generator. And you're going to find the code between them is also extremely similar. Okay, let me go back to a new Rhino thing. I don't need to look at this anymore. Okay, finally, we're in perspective mode. Love to see it in 3D. Okay, one thing that we need to first do is generate the points grid. Initially, in this one, we're using this square grid component and getting the area and dispatching or whatever. What we're going to do is get some sliders. That'll be 0 to 100. These are going to be our X, Y, and Z, just like how we have for the other grids. So I'll copy paste that twice. Change this one to Y. Change this one to Z. Make them all different. Maybe I'll make them lower in case I mess up. I don't want to overdo my computer, blow it up, and crash or something like that. I don't know. And we're going to need a visual size, cell visual size slider as well, just like how we had last time. Cell visual size. Okay. I'm going to do this in two ways, just so you can see. This is what I was previously doing. We're going to get a C# component and get 4 on there. We're going to change that X to a capital X, change that Y to a capital Y, change that Z to a capital Z, change the U to size. These are going to be an int. X, Y, Z are ints. And size is a double. Plug is incorrectly. Okay. And this is just how I was doing it. But I'm going to show you an alternative way without C# in just a sec. But this is like, I don't know, one way to do this. We need to create a 3-dimensional grid of points for us to dispatch and then move our cells to, just like how we were in the last one. So data tree point 3D P tree new data tree point. Then we're going to have a triply nested for loop here. For int x equals 0, x is less than big X, x plus plus. For int y equals 0, y is less than big Y, y plus plus. For int z equals 0, c is less than big Z, Z plus plus. Then we say GH path, we have to make that address, PTH, equals new GH path. And it's going to ask us for the index on this, and that's going to be X, Y, Z. That way we can address each point in its unique address in the grid. So we have those 3 coordinates to address each point in the grid. Then we will say create the point 3D PT equals new point 3D. And that's going to be at, in real world coordinates, these are going to be the coordinates X times size, Y times size, Z times size. Then we say PT or P tree dot add pt point to path. So A equals p tree. And you can see now, as I increase our cell visual size, why did that? Oh, I did this incorrectly. Max. Okay. You can see our cells, our points move around. And if you look at our data tree, there's only one item at each address in the data tree. And you have those X, Y, and Z coordinate indices. This is different than how we had it last time, where we had each row has multiple items in the list. It's just easier in 3 to address each one individually like this and make your data tree this way. This is how I prefer. So that's our point grid, but you don't actually need to use C# for this. We can do it the same way we were before. You just take the size and the extent x, y into a square component, just like how we had before. Then you get the area. Then you get a series. You stick the step into the cell visual size. The count is going to be the Z amount. We're going to simplify and graft the centroid output, get a Z, unit Z factor on the series, and then a move component. And we're going to plug centroid, the motion, and then we graft the output. And if you mouse over this, it's the exact same data layout as the C# component gave us. So that's just a way to do this in regular components. We've got our nice little data tree where everything is at its own little address there. 0, 0, 0 is just 1, 0, 0, 1 is just 1, etc., etc. So that's just 2 ways to do that. I used to do it with the C#, but now it's like, I don't know. I think people prefer probably seeing it in Grasshopper alone. Okay. We need to copy this. I'm going to leave the C# one there alone. I don't need it. Disable that. I'm going to group these and call this points grid, so I know what that is. I'm going to grab our 3D rules generator, bring that down. I'm going to take our last 2D CA one, copy that, paste that. Anyone know if there's a way to copy paste a component without bringing along all the things it's connected to? I'm sure there's like a shortcut for this, because now I have to disconnect each one. I bet there's a way to do this better than I'm doing it. You guys are going to be surprised at how fast the 3D CA builds off the 2D CA. It's like only maybe 60 lines of different code, which is pretty funny. Okay, we can now connect everything how it should be. So here, the X goes to X, Y goes to Y. We got to add one more for the Z. Make sure you change that to int type. Don't forget. I'm just going to grab these sliders because they're already filled out. Initial mode, initial chance, button, trigger. Take those. Oh. Why does this thing work like this? I hate this component, the trigger component. Set your interval to 1 millisecond. All right, now we hook it all up again. Seed, mode, chance. Enable these things. I'll pause that. Okay. You're set up to make our 3D cellular automata, our real 3D cellular automata, not like these phonies on YouTube. Okay. Let's do it. Well, first, I guess I do want to visualize it, obviously. So let's do that same center box thing. Ugh, gotta go back up here and grab it. Simple mesh, move to point. We got it. Let's go. Bring it on down. Divide our cell visual size, make those simple mesh, move the geometry to these points. How's that look? Looks good. All right, so now we can at least see our voxel grid. Does that look right? Yeah. So now we can at least see our like voxel grid in a way. And when I get to dispatching, that's when it'll look cool. So I'll put a dispatch. And I know I'm going to be wanting to dispatch these guys. Check that data tree. And I'm going to be dispatching it with that. Okay. So currently it's not really displaying correctly because it's still doing the 2D cellular automata, but with like 3 inputs and things like that. So it's not going to be exactly correct until we get in there and fix it. All right, so pull up my code over there. All right, hop in. Obviously, first things first, change this to say 3D CA. And we're almost done. No, just kidding. All right, so everywhere there's an X and Y, you're going to want to basically add a Z. So Z. Come down here. We're going to want to add a int Z into our initialized grid. We're going to want to add a, all right, we'll take it one step at a time from there. So nothing in the main thing really changes except we're creating the next grid using the current grid, but now we have to include the grid dimensions because it is hard to get those from a 3D data tree. What do I mean by that? See, we previously just passed in the grid, and then we said, oh, int columns equals this, and we got that from the grid, and int rows equals this, and we got that from the grid. It's actually really annoying to do that in 3D, so we're just going to pass along our x, y, and z dimensions into this function. X, y, z, and that way we don't need to try to do that. And that's the only difference in this section of the code. Okay. Come down a little bit. We'll skip the initialize stuff for now. Here's what we're going to do. I'm going to delete this other mode, and I'm going to delete the if mode block around it. We'll return and make some new versions of the initialization later, but for now, we'll just keep it with the all over random initialization. So this GH path line here, I'm going to cut, so Command X or whatever, Control X, and we're just going to triply nest all of this in here. For int z equals 0, z is less than big Z. There. Okay. And then we're going to put the GH path, whoa, why did that come out over there? Right there. And it's going to be X, Y, Z. Okay. So what this is saying is just the same. We're going to initialize the grid with random true or false values for our 3D grid now, because now we have 3 coordinates, X, Y, and Z. Great. Guys, we're halfway done, almost. Not even kidding. This is like much easier to add this on. We don't need this anymore for ease of use because our generate is going to take in X, Y, and Z. So let me actually add that there. Int X, int Y, int Z. And those are capital. So we don't need this anymore because columns is equal to X and rows is equal to Y. And then whatever depth is Z. Okay, so to create that temporary grid, we first need to triply nest this, and that means we're going to move this GH path, cut, paste there. It's going to be X, Y, Z. We add that Z loop for int Z equals 0, Z is less than Z, Z plus plus, and we add last bracket. Also, don't forget to change columns to big X, rows, Y. So now we've got our 3D temporary grid. And here's our main loop where we're looking at every cell and its neighbors. Well, you can guess that we're going to first change columns to big X, rows to big Y. You can guess that we're going to add another layer to this loop here, the Z layer. Z is less than Z plus. And all the way down to the bottom here, we're going to add, that extra bracket so we don't get messed up there. Okay, pretty much the same. We're going to proceed in the same fashion, right? Counting the neighbors. We're going to keep track of the true neighbors for the current cell, count all the true neighbors in a 3 by 3 by 3 grid, including wraparound through modulo magic. So now we're going to add another level to this inner loop here. We're going to have for int k equals -1. K is less than or equal to 1, k plus plus. This is going to be pretty similar, except instead of columns, we don't have that anymore. We have to replace that with X. We have to replace rows with Y. And we actually need to first create the address for this, right? We need to get that path. So we need to create the path for each of the 27 cells in the neighborhood. Remember, I said 27 because that is including that center cell, just because it's easier. So how are we going to do that? We're going to say GH path, neighbor path, new GH path. And inside that is where we're going to put basically this type of thing. Instead of addressing it in the direct conversion there, we're going to first make a path to it and then get that. So new GH path, open parentheses, another open parentheses, X plus I plus big X, close parentheses, modulo big X, comma, open parentheses, Y plus J plus Y, close parentheses, modulo big Y, comma, Z plus K plus big Z, close parentheses, modulo big Z. Let me make sure I wrote that right. Yep. So that's just like how we did before. It's going to get us the correct address, index of the cell, including if it's on the edge and needs to wrap around to the other side or whatever. All right. So we create the path for each of the 27 cells. Then we add the cell state to neighborhood. We can now delete that because we've got this here. So what are we going to add? We're going to add grid. Then we're going to open bracket and say neighbor path, comma 0. That's just saying, since there's only one item at each index, we have a unique index for each item in this 3D data tree. This is just saying get the first item at that index. And since there's only one item, it's always going to be 0. So go to this address and grab that item, is essentially what we're saying. And then convert it to an integer, this is true false value currently, and then add it to the neighbor count, just like we did earlier in the 2D version. All right, and now obviously we have to subtract the cells, the current cell state, since it was included in the above neighbor chain loop, right? Just like we did before, but now we need to get that path, right? So GH path current. No, I'm just going to call it current. GH path current equals new GH path 2 open parentheses X plus big X, modulo X, Y plus big Y, modulo big Y, Z plus big Z, modulo big Z. That is the current cell's address. And then we say neighbor count minus equals grid current 0. Okay. So that's just like how we did. We just have to address these cells a little differently in 3D. All right. And now we're really almost done. Check the neighbor count against the birth survive rules. So instead of this grid dot branch x index y, we just say grid current 0. And we say temp grid current 0. And we say temp grid current 0. Come on. And we say temp grid 0. And that's it. That's all it takes to create your 3D cellular automata once you already have the 2D cellular automata. It's actually very easy. All right, we've got that all there. Let's visualize it in like a nice way so that I can see without these like weird see-through stuff. Preview, geometry to preview, material I want to preview it with. Let's check it out. All right, so yeah, you can see that one has no survival rules. I mean, it's pretty much looking really, you can't like tell. How can I tell if this is working correctly or not, right? Kind of hard to. So just like how before when we debugged it using Conway's Game of Life, because that's a known rule with known formations, we're going to do the same thing. We're going to look up 3D cellular automata rules. Oops. Rule. And if you can get this link here from softologyblog.wordpress.com, pop that in there. This guy, he's got this really cool software called Visions of Chaos, but he kindly enumerated plenty of rules here. And there's some that we can try out and test, because I know what they look like, so we can make sure that our thing works right. Here's one called Clouds 1. It's quite annoying to type these all in. That's the other thing. Just because like Clouds 1, this is how it looks. The way he has this formatted is survive, then birth, then he says the number of states, then he says the neighborhood type. So you read this as the survive rules are 13, 14, 15, all the way through 26. The birth rules are 13, 14, 17, 18, 19. There's 2 states, and it's using the more neighborhood. So we're already guaranteed we have 2 states, and we're using the more neighborhood. So let's input these values into a couple num components so that we can test out whether our cellular automata in 3D is working as we hope it is. Okay. So for the birth rules, let me just make sure. He listed them survival birth. I don't know why. I think so. Yeah, he did. Okay, so for the birth rules, we have 13, 14, 17, 18, 19. So you can imagine that it's a lot more annoying to write these custom rules because there's just so many more numbers you have to write. And then for the survival, we have 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay, now I can up my initial chance. Yeah, look at this. Okay, let's increase the size of the grid, but not too much, because it's pretty heavy when you get higher up in numbers for things. And when I do this, yeah, this is working perfectly. So clouds is what this rule is called, clouds 1. It sort of makes these like structures that erode over time. And so this is working exactly as it should. Oh, what am I doing? Sorry, guys. Rendered mode. Make it look really nice. So there it is. There's clouds 1. That's looking really cool. Go to that page and look for any of the ones that end with /2/m and input them here. Or obviously you can just use this. So you can search around and try to find some cool rules with your rule generator, but it's kind of also cool to just check out some rules that you know exist. And there's not really an analogous one to Game of Life. A lot of the rules in 3D either explode or die out. They don't really persist like that. And one thing that we should now go back and do is add back in these initial modes. Because in 3D, it actually really matters a lot for if you have certain initial modes, like certain rules just like won't work as well. And I want to get us some nice symmetrical, really cool looking ones. So we're actually going to have 4 different initial modes here. So we can edit this to be 1, 2, 3. So 0, 1, 2, or 3, okay, for our initial mode here. And here's what I'm going to do. Hop in to our code. Pop it up in my other window. All right, so if mode is 0, we'll do this. And that is all over random, right? That's just like random all throughout the grid. Else, if mode equals 1, we'll do something else. And I will copy that a couple times. 2 and 3. So we'll have 4 initial mode settings, basically. Initial mode 1 is going to be a centered single cell, just like how we had in the 2D version. Okay. Here's how we will do that. I'm going to copy this from the all over random. So we use a lot of that code. And we just replace this, right? I don't want to type this. I'm just going to put it in the chat. Right, this is what needs to go into that thing. Kind of annoying to type, right? As you can see, I don't want to type that at all. So I'm just going to copy and paste that. This is just so that it's that this evaluates only to true if it's that single cell in the center. Okay. Let's test that, right? Let's make sure that that works. Initial mode 1. Let's try with some random rules. A lot of them are definitely going to just flash because they are not very congruent with surviving. There we go. We got a cool one, guys. So starting off from one thing, you get this nice symmetrical thing. But also keep in mind, if you're on an even numbered grid, it's not going to be even once it gets to the edges. So let's change these to an odd number. Because how can you have a single centered cell on an even numbered grid? You can't. So you can get some really cool 3D cellular automata. So the difference between this and the stuff those people say is a 3D cellular automata is vast. This is a true 3D cellular automata, not a 2.5D cellular automata, which now you know the difference between. And we can make some really cool stuff. Yeah, look at this one. Like flashes between different, sometimes get really cool rule. Look at this. Sort of stabilized. Well, anyways, you get really cool forms from this. All right, so that's our second initial mode. Now, what if I want, say, a centered solid cube? Like instead of just one single cell in the center, what if I want it to be like 3 or 4 side length solid cube in the center to start from? That'll give us different results. Different patterns won't, certain patterns won't work with just one single cube. It'll instantly die. But if you have like a 4-side cube, that'll work. Okay, so the reason I say 3 or 4-side length, if your grid is even, it's going to be a 4-sided cube. And if it's odd, it'll be a 3-sided cube. That way it can stay completely centered, so you get a fully symmetrical growth, right? So use the space to write. Depending on if grid is even or odd in each dimension Z. So we have to check that. So we'll use some temporary integers A, B, and C. If x modulo 2 equals 0, this is basically checking if the grid size is even. A equals 4, else A equals 3. I'm going to copy this. Change this to be Y. I'm going to change this to be Z. I'm going to change this to be B, and this to be B, and this to be C, and this to be C. Okay. So now we have A, B, and C as either 3s or 4s, depending on the size of the grid in those dimensions. We're going to jump up here and grab all this code because I don't want to write 3 for loops again. And here we go. I need to X out all this. All right, so what's our if statement here to decide whether a cell is turned on or off, right? It's going to be quite a bit of writing that I don't want to really write out myself. So once again, I'm going to post that into the chat because it's like pretty annoying to write that. But here, it lines up really nice so you can see what we're doing here. If x is greater than or equal to x, the x dimension grid, blah, 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 minus a divided by 2, and x is this, just know that this is going to center a cube. This only evaluates the true for these dimensions, whether it is inside of this sized cube in the center of the grid. That's all it is. It's just like very annoying to type that all out. You know, I don't want to have to type that all out every time. And now if I go to this, you can see we start off a little differently. Here, let's get a different tool. Oh, so, yeah, look at that. That's cool. So this is going to work to make symmetrical forms in 3D more reliably than the single-centered cell, just because more rules will be able to grow off of the initial starting condition of a 3 or 4 side length cube. And you could change that size. You can make that a slider into the component, whatever you want. You know, if you want it to be like 5 or 6 side length or 2 or 3 side length cube. So we get some really interesting stuff happening. Look at that. Very nice. Okay, and our final initial node is going to be a centered random cube. Sorry, guys. Zoom in. Of 3 or 4 side length. When I say random cube, currently it's just a solid cube, but now we're going to say like, oh, some of those cells could be deleted or something. So it won't be a fully symmetric starting condition. So I'm going to grab all of this from the last thing I wrote, that centered solid cube code, paste that inside here, and then I have one more sort of condition after this if statement, where I say if rand.next double less than chance grid.add true path, else this. Gotta add one more bracket there. And then I say else grid.add false. This is basically saying, okay, so if this is true, so you're in the centered cube of 3 or 4 side length, then we do another check where it can randomly be on or off, and other than that, they're all off. Okay, and we're all set here. So now I'll show you what that looks like. Oops. So the initial starting condition is a randomly sized thing, so you won't get perfectly symmetrical stuff. So I like this one a lot because you get really cool forms here, sort of architectural. Let's see, get a cool rule here. Nice. So you know, you get some really good stuff there that way. All right, 34, 334. All right, this is the final 3D cellular automata. So let me 3D CA, completely done. Save this. I'll share this with you guys in the chat. Okay. There's that. So that includes all of the 1D, 2D, 2.5D, 3D, all of it. What else can you do? Obviously, we've got more further exploration that can be done. A lot of it's pretty much similar to what I said in the 2D. But you could have, you know, I don't know, cyclic in 3D, this in 3D, abelian sand piles don't exist in 3D, I don't think. That would be some crazy stuff. Could you do a subdividing automata instead of a grid? So maybe you start with one cube, and then that breaks into 8 other cubes, one for each corner in the cube. And then depending on if those are alive or not, it checks out the other ones, and then you subdivide further and further. So instead of having an existing grid, you create further and further subdivisions of that grid. Could you modify this to always produce connected voxel regions? So I don't want to see any floating little cubes or none that are connected like this, how it's only connected by the diagonals on the edges. What if I always want it to be connected by faces, so it's a fully connected voxel region? What if you wanted to do that? What if you wanted to, could you automate the process of searching for interesting? So can you somehow quantify or give a score to a rule that is interesting to you, and then like have it loop through different ones and then like save the ones that are interesting to you? That would be something really worthwhile because there's so many rules to explore, and just clicking this button, a lot of them are just going to be bad and not look cool. But then there's a lot of them that will be cool. And if you have different neighborhoods, that even changes it too, because you have all these different rules you can explore when you change your neighborhood. So there's lots of different further explorations we can do. Mike, is the Q&A supposed to be in the last half hour from now to 4, or is it from 4 to 4:30? Because I have another thing I could do if we have time, or I can stop. What did you say?
Keep going if you want.
Okay, great. So we got a little bonus here. It's not a 3D CA. It's another 2D CA, but it is called rock, paper, scissors cellular automata. So what we're going to do is put down a C# component, and it's going to have 5 inputs. And we're going to call them. First one is going to be threshold. Second one is going to be capital X, then capital Y, then seed, then reset. This one's cool. This is a cyclic cellular automata. So there's going to be 3 states in this automata. And it's actually going to be pretty quick to code. Let me see here. Threshold is an int. X is an int. Y is an int. Seed is an int. Reset is a bool. All right, let's fill these out. Threshold is going to be 0 to 4. So 0, 1, 2, 3, 4. X, you know, I don't know, or something. These are the size of your grid, obviously. That, get Y. Seed is going to be, you know, big number. Reset is above. And change that to be 1 millisecond. All right. All right, I'm going to try to rush through this one so that we don't take too much time. I'm not going to rush through it, but I'm not going to explain it as much as I did the others because we're going to consider this a little bonus. It's not, wasn't on the menu, but it is now. Okay. All right, we're going to hop in here. Window there, zoom in. Like a lot of the other ones, we're going to keep our random down here and our data tree. Integers this time because it's not just on or off. We have 3 cell states in this, so it's going to be like 0, 1, and 2 are going to be our cell states. Okay, so we're going to say grid. We're going to say data tree int grid equals new data tree int, and I'm going to explain exactly what we're doing here. I call this the rock paper scissors automata because that's what it's called. So let me explain what that means. Right? 0, rock. So the states are going to be 0, 1, and 2. 0 equals rock. And that beats scissors and is beaten by paper. 1 equals paper. And that beats rock, beaten by scissors. 2 equals scissors, beats paper, and is beaten by rock. You guys have played, I'm sure. Maybe you call it something else where you're from, I don't know. You know, rock, paper, scissors, that type of game. We're going to do that with a cellular automata, basically. Up here, we're going to make our component.message equals RPS. That would be rock, paper, scissors. You can call it whatever. Obviously, we're going to have our reset block here. If reset, we want rand to equal a new random using the seed. And we want our grid to equal initialize grid, just like we have. We haven't defined this yet, but we will. So that function is coming back. And then every time we run it, we want the grid to equal generate the next generation, right? And that's going to take in our current grid and the threshold value. And we're going to output the grid. Okay. So we have 2 functions we haven't defined yet, initialize grid and generate. Pretty common though. I'm sure you're familiar with this by now. Give myself some space to write in. All right, we know we want to initialize the grid that's going to be a integer data tree, right? So public data tree int initialize grid int x int y random rand. That's what it takes in. Okay. Well, we need to output a data tree, so let's make one. grd gird equals new data tree int. And in the end, that's what we're going to output. So let's say return grd grid. Okay. So now let's loop through every space and assign it either a 0, a 1, or a 2. Okay? So for int x equals 0, x is less than big X, x plus plus. For int y equals 0, y is less than big Y, y plus plus. For every x, we're going to create a new path. Gh equals new gh path x. Okay. And then here, this is where we're going to either assign a 0, a 1, or a 2. So first we need to create a random number to test against for percentages. So double test equals rand dot next double. Okay. Now here we go. If test is less than 0.333, like 1/3, you know, we're going to do this. grid.add 0 to that path. Else if test is greater than or equal to 0.333 and test is less than 0.666, grd.add 1 to that path. And you can guess what's happening next. If test is greater than or equal to 0.666, grid.add 2. Okay. And that is our initialize function all set there. So this is going to build a data tree, int data tree with zeros, ones, dang, what am I doing? And twos. Okay, great. All right. Now all that's left is to create our generate function, which is not too hard. Public data tree int generate. And it's going to take in the current data tree and the threshold. Okay, what are we doing in this? We are loop through every cell. We are going to count the totals of neighboring cell types each. So it's going to count how many rocks are near it, how many papers are near it, and how many scissors are near it. And then it's going to decide its fate, oh man, in the next grid. And then update the grid. Okay. We're going to do this again for ease of use. We're going to get the columns equals grid.branch count. Nope. And the rows 0.count. Okay. Now we need to create new grid and fill with the current values. So this is going to be looking at the grid and creating this grid to operate on. Data tree int new grid equals new data tree int. For int x equals 0, x is less than x. Oh, sorry, x is less than columns. I'm so used to that. X plus plus. For int y equals 0, y is less than rows. Y plus plus. In here, we need to create that path. Path equals new path index x. Okay, if grid.branch x index y equals 0, new grid.add 0 to the path. Else if grid.branch x y equals 1, new grid.add 1. So this is just basically copying that first that original data tree into this one that we're going to operate on inside the function. Okay. All right, now get a little barrier in my code, even though we're still inside that main function. I'll make it smaller. Main loop, where we look at every cell and count its neighbors up. All right, so this is our main 2D loop here. So for int x equals 0, x is less than columns, x plus plus. For int y equals 0, y is less than rows, y plus plus. give ourselves some room here. We know that we're going to return new grid at the end of all of this. Okay. So, for counting neighbor types, you're going to need to keep track of that, right? So int r neighbors, that would be rock neighbors, equals 0. Int p neighbors equals 0. That's paper neighbors. Int s neighbors equals 0. That's scissor neighbors. So that we can count for each cell how many of each type of neighbor its cell has, right? Add up all the states in a 3x3 grid, including wraparound modulo magic. For int I equals -1, I is less than or equal to 1, I plus plus. For int j equals -1, j is less than or equal to 1, j plus plus. We can skip the current cell value by doing this. If I equals 0 and j equals 0. So this is what I didn't do in our other cellular automatas, where I had to subtract the current cell count out of there. I just am going to do it a different way here. Just continue. So skip the current cell value. Don't take it into account. All right. If grid.branch and we're doing this annoying indexing thing again, x plus I plus columns, modulo columns, at index y plus j plus rows. Parentheses here, sorry. Plus j plus rows, percent rows equals 0. Neighbors plus. So if that neighbor that we're looking at is a rock, we add up the rock neighbor total. All right. Now I'm going to say else. I'm going to copy all this. Else if grid.branch blah 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 percent rows is 1. Paper neighbors plus plus. And scissors neighbors plus plus if it equals 2. Okay, so this is us looking at every single one of those neighbors, checking its type, and adding up the total of its appropriate type. Okay. One last little section left. Depending on the current cell type, check neighbor type total against threshold, but only check the neighbor type that beats it. So if it's a rock, I don't need to check the scissors neighbors. I only need to check the paper neighbors. Okay. Here's how this works. If grid.branch x index y, the current cell, is 0, if it's a rock, cell is rock. If p neighbors, because paper is the only one that beats rock, is greater than threshold, the current cell is going to become a paper cell in the next one. We do that by saying new grid branch x index y equals 1. The cell is okay. And then I'm going to copy all this. If it is 1, and that's paper, the cell is now. Aha, sorry, I almost messed up there. If the scissors number is greater than threshold, the cell is now scissors. And we'll do that one more time. Okay, sorry, sometimes I just get confused when I see so many nested things. You have to make sure they all line up. Okay, if the current cell is scissors, cell will change to rock if the number of rock neighbors is greater than the threshold. All right, and we're done. Let's make sure that that doesn't break. Nice, that's looking good. Now, all we need to do is visualize that. I'm going to cheat here and just copy it from my other Rhino window into this window. Sorry, guys. It's nothing new. It's just the same symbols and square grids that we've been looking at. And X and Y. And A comes out to, so this is a data tree in A where every number is either 2, 0, or 1. That's going to come into here. We're going to check it for equality with 0, 1, or 2. There, and I'm going to zoom in. Okay, let's check it out. Uh-oh, what's happening? Well, it's actually pretty expected. We have to up our threshold. So I set threshold to 2. We can get away with a lot bigger grid than this. See something really cool here. Ready? Cool. So what we're seeing is red beats green beats blue, or maybe it's the opposite. I'm not sure. But basically, these things are rocks, paper, and scissors, and so they're all trying to like devour and convert the cells next to it to their type, but they can only beat the certain types. Yeah, it does look like reaction diffusion patterns. Certain reaction diffusion patterns definitely form these spiral-like shapes because it's very stable. But what's really cool is we can change the threshold value. So the threshold value is saying, if I'm a rock and I look at my 8 neighbors around me, and I find more than 2 papers, I get converted to a paper. But if I lower this to 1, what do we get? It starts to change shape. You still get these spirals, but they're different. And if I set it to 0, you get even these tighter spirals, which are really cool. And if I set it higher than 2, what's going to happen? Well, let it smooth out a little bit first. If I set it to 3, it actually mostly stops and reaches a stable configuration, which is pretty interesting. And I'm sure if you thought about it, it would make sense why that is, but I don't feel like thinking about it. So really the cool number is 2 for the threshold, or 1 or less. But if you started off on threshold 1, you're not going to get anywhere with it. And same with or threshold 0 or 1. You need to start off on threshold 2, let it start to form these stable spirals, and then you can mess around with the threshold and get some different ones. So this is a really cool thing. What I would hope you guys do, take this, and what if you made this 2.5D? And then what if you only looked at what the rock looks like over time, or what paper looked like over time, or just 2 of them over time? We'd have this like crazy tower with like these weird shaped voids from these things like swirling around over time in 2D. So the 2.5D version of this would look really cool. And definitely, there's nothing stopping you from upping this into a 3-dimensional rock, paper, scissors automata. And that would probably be like so cool. I haven't actually done that yet, but I'm sure that would look really cool. There's definitely, I think there's videos of that on YouTube if you search like 3D rock, paper, scissors automata. So this is a little bonus. I will add that. Bonus. And I'll put that into the chat. Bonus done. So that is a 3-state cyclic automata, where each state like loops back to another state. So like rock beats paper, beats scissors, beats rock. You could add more states to this. You could have 5-state cyclic cellular automata, 4-state, whatever. You could do it in 2.5D or 3D, anything you want. But this is one of my favorite types of cellular automata. It looks very cool, and it's just cool how it forms these spirals that are stable. As you can see, like red is eating blue, is eating green, is eating red, and they just like spiral like that, and that's why they form these stable spirals. And sometimes if you leave it long enough, you'll just get one big spiral or two big spirals. Yeah, it is similar to that type of reaction. All right, guys, that is the end of the automated automata webinar. So if we've got some questions, we can do a question and answer session now. Look at that. Almost 5 hours exactly on the dot. That's pretty good. All right.
Too good. It was just exact.
Yeah. Thank you.
Yeah, perfectly timed. Yeah, that was awesome, as expected. Does anyone have any questions that I didn't answer? Or if you want to, we could even bring you on to voice and video if you want to ask that way.
But if you're shy, it's okay. You can just do it.
If you're shy, it's okay. If you want to do that, you can just click the raise hand button. If not, you can just ask the question.
I'm sure you guys have some questions. Don't be shy. Come on.
In the chat.
Where, how, when did you learn coding? Do you recommend any course or book? It's a great question. I taught myself C#. Basically, I did it by searching on YouTube for like Grasshopper oriented tutorials, just because I knew that was what I wanted to apply it to. And I find that if you just search like C# tutorial, it's going to be like really boring stuff, like how to edit a string of numbers, or a string, or like how to do something in like a database. So I looked it up and I learned through like Grasshopper oriented stuff, which was actually really helpful for me to keep engaged with the subject matter. So there's a couple of things I would tell you to check out on YouTube if you're trying to learn C#. One is GSD 6338. Search that on YouTube. That is a course by Jose Luis del Garcia Castillo. He is a professor at Harvard School of Design, and he did this course, GSD 6338, where they are learning C# in Grasshopper. So it's like a computational design 101, and they do C# in Grasshopper, and they do a ton of stuff. Another one is if you search Long Nguyen C# Grasshopper on YouTube, you'll find a popular one that's like a mesh growth thing that you write. So he walks you through how to create this like mesh growth thing. He has another one, but it's a little harder to find. So if you search GSC 6338, and if you go through that whole course, you will come out the other end understanding a lot more than like, I don't know, that's probably the best one, is GSC 6338, but it's pretty long. There's a lot of videos. And then Long Nguyen C# Grasshopper is another really good one for foundational.
We have them both on our website here.
Oh, nice.
Resources.
Perfect. Yeah, those are really, really good. Are there any limitations to using the GH Python component versus the C#, or should it be straightforward to translate? I think you could probably do all this with the Python component for sure, and I think it should be pretty straightforward to translate. If you're good with Python and C#, you can definitely do this in either one. I just do C# because that's the language that I feel more comfortable in than Python. Plus, I think it's a little faster.
Plus, it's also like, it's the native language of Grasshopper, so I think
exactly.
There's less like loops you have to jump through to like get things and like libraries and stuff like that working.
Did it take too long to learn? No. What's long? 2 years, I guess, 2 or 3 years now. But I felt at first it's really hard because you're just like blindly following along with things and not really understanding. Like, somebody types like public void and then like a function, you're like, well, what is public and what is void? What does that mean? And they don't explain it. And they're like, you'll worry about that later or something. They'll say that in the tutorials. And you're like always just wondering like what that type of thing means. And it took me like maybe 6 months to 8 months before I started to like feel comfortable myself and like really understand all parts of like coding in a way that I felt comfortable. So at first you're sort of floundering and just like blindly following along with things, but then eventually you start to like understand through experience. And then at like the 1 year mark, if you're coding frequently, you'll really start to feel comfortable and start to take off and you're learning like a lot.
Yeah, I just learned it from the internet. Can't really learn coding from a book, I think.
Yeah.
For me, I mean, you just have to just start doing it.
Yeah.
You don't really read anything. I mean, the whole time you're doing it as you're learning about it. So it's not like studying for a test on like history or something where you just have to remember the information. Like your fingers need to remember the information. Like you have to just do it. Wow. Like you shouldn't ever be learning code without the computer and keyboard and software open in front of you.
I think learning from a book is probably like the worst way you could learn to code. Probably you know watching like videos or looking at other people's code is definitely a better way to learn that.
And it's not unnecessary. I mean the whole doc thing is documented online. Right? So it's not really necessary for that. Yeah. And like things are always updating and added. And, like for C#, they're always adding like new codes and new processes and new.
Yeah, there's actually like link LINQ. Like if I didn't use anything besides the basic C#, but like here I could have put like using system dot link, and then that could have made like so many of these like loops and stuff way shorter lines of code. I could have done things a lot faster or like with less lines of code that way. But I don't know. I just wanted to keep it basic C#. Oh, one thing I almost forgot this. This won't even take 1 second to show you guys. If you want to improve the speed of this code, you can easily parallelize it really easily. Cellular Automata is like a perfect candidate for parallelizing your code because you can loop through all the cells and it doesn't affect any other cell if you go out of order. So if you do system.threading and using system.threading.tasks, you can now access the I don't know, whatever it's called in the like parallelized for loops. So okay, so this one. If I come down here and I add, and then I change these for loops to be parallel for loops instead. So I say parallel. Sorry, let me zoom in. If I say parallel dot for, and then I say 0 x equals that in bracket, and then I copy this for y, and I copy this for z, and then I come down here and I uncomment these. Now we have parallel for loops for our 3D cellular automata. And it goes a good bit faster. So this was at like 100 milliseconds per iteration. Now it's like half that. So that many lines of code improves the speed of your thing a good amount. So now if I increase this, you'll get greater returns with your parallelized for loops at higher grid sizes. So all you have to do is add these using statements and then change your main loop from regular for loops to these parallel for loops. And then at the end of the bracket, you have to close it out differently. But that's one way that you can improve this. And it's just like, you might as well do that because it's a lot faster.
Yeah, parallel, I think.
And if you compile these components, that would really be a lot better too. because it goes a lot slower in the C# Crypt components. But if you went into like Visual Studio and made this a real compiled component, it would be even faster. Yeah, the parallel syntax is really weird. That's why I don't like to write with it. I'll write it normally, and then like if I think it's worth it, I'll go back and change it. But it's weird to like write them just off the bat.
I use it sometimes, but that's another thing actually what you're just talking about. Like with Python, it's not compiled code, so that's also like Python runs. It has to compile each time it runs.
Yes.
So that's the big reason why Python is like slower sometimes. It's
exactly
compilation. Yeah, I multi-thread sometimes, but sometimes I don't, because the one thing about Grasshopper that I think they're doing Grasshopper 2 is like the whole process isn't multi-threaded, like just components are multi-threaded, so it's like it's not really as efficient as it could be, I think, you know?
Yeah.
Like for instance, when you do something in Houdini, let's say, like the whole network is multi-threaded as a process, you know, rather than like pieces, like nodes, you know. So
yeah, right. I got you. Yeah, because it's just this component that's doing that. But if the whole canvas, the whole solution was parallelized, it would be a lot better.
The whole solution was considered as one code and then parallel.
Yes.
Anyway.
That would be nice. Guys, any other questions? Yeah. I hope I see some really cool renders of things. And this is just the start too. This is just the basics, you know. This lays the foundation for using these cellular automatas in architectural engineering or design purposes. But you can go a lot further with it and make smarter types of cellular automata. Like this is really just very exploratory. Like you get to choose the rule and then see the output, but you don't really have so much control over it. Like there's certainly ways you can construct cellular automatas that you can like guarantee that you have connected voxel region or something, which would be useful if you're making something that you need to 3D print, so that's all connected parts. CB says, is it possible to stop a trigger after a specific number of iterations? Yeah, there is actually. We could have done this a whole different way, where instead of having the trigger component, I could have had another slider that was like this, and then I just called this iterations, and then I could plug that in over here, and then in the loop, I could say, you know, in here, I could put this in a loop that says for int I equals 0, I is less than iterations, you know, and then it'll only run that many times. So instead of relying on the trigger to stop it, you could just add an iterations input or like a limit input, whatever. If you don't want it to be the same name as this output, you probably shouldn't. Then you can just have the thing stop exactly on that many iterations. Any big difference between your code and the Rabbit plugin? I had Rabbit once. I don't really remember. I actually remember really hating Rabbit a lot because I really didn't like the way that it worked. I thought it was like really weird. Is it not on here? Okay, you have to get it from a different website. That's cool. Always cool when somebody doesn't put their plugin on Food for Rhino. Don't know why they do that. Well, yeah, here's one big difference. They call 3DCA 3DCA, but it's actually 2.5 DCA. So that's a big minus in my book, that they claim this is a 3D cellular automata, but actually it's a 2.5D cellular automata. Plus they say it's a Conway's game of life. So I don't know, does that mean that they don't generalize it to use other birth survival rules? So it actually seems like it's a lot more limited than what we've done here today. Although, you know, they have these other things. They've got L systems and stuff. But I think what we've done, you know, they don't have 5 neighbor one-dimensional cellular automata. They only have 3 neighbor one-dimensional cellular automata. So we have way more patterns we can get from that. And we can do any 2D cellular automata, not just Conway's Game of Life. And we have true 3D cellular automata, not this 2.5D nonsense that I'm always seeing. So don't use this for cellular automata, but use it if you want to use L systems. Instead, use the stuff you learned today to make your own cellular automata. No boycott, but it's such a pet peeve of mine when I see
Also,
3D
Rabbit's
cellular automata and it's not.
pretty old, right? I mean, when's
Yeah,
the last
yeah.
time this thing was updated? It's probably one of the first plugins I ever saw.
Yeah, I had it I had it when I was like using Rhino 5 or something.
I don't think it's been updated since like Rhino 4.
What's the main difference between an L system and a cellular automata? They're just totally different systems, I think. They're related in that you like start from like different inputs and it follows a set of rules, but that's actually true of so many things. That's like basically the basics of a Grasshopper script, right? You put in an input and follow some rules and get an output. I think that's really the main similarities. The difference between a cellular automata is just like discrete values in some type of grid, and you're looking at them, and then you adjust your state based on that. An L system is like not usually grid based. I don't think it has to be. And it can be lots of different types of geometries, like it could be blocks or lines. And then you select like an angle and it branches off of that. And then every branch will not branch at that same angle. And you get like these fern or tree-like structures. So I'm not really sure it's apples to oranges, I guess, Two different things. One thing I should probably mention is really cool. This guy, Jadiminus Hirdaicus, cellular, what does he call it? Marching cubes. This guy, Jadiminus Hirdaicus, has created these, 2020 element. These are really great. This is how I made, man, I hope I can find this. Nah, I'm not gonna look through. That latest image that was posted yesterday by Design Morphine, that was like on the Instagram. This image here, I don't know if you can see my phone screen in the Zoom. This image here, I created a 3D cellular automata, and then I took those point values for each corner, and then I used this guy's tutorial where he makes these custom marching cubes library, and you can like, here we go, look, you can see here. You can like clad a series of points with these crazy, more detailed geometries. So you first generate the library of the cool geometries, and then you like cover the points with it. So you can get some really, really complex looking structures using that technique. And you can like really like hyper detail. So you go from like the voxels, like these, to something way, way, way more detailed that is like really crazy to look at, because you replace like every one of these faces of the cubes with something way more detailed. So look up this guy. I really like his tutorials. They're really great. And this is a really good one to apply to cellular automata outputs, 2.5D and 3D. How do I apply cellular automata to my daily work? Well, I really like to explore different cellular automatas in different types of ways, as you can see, obviously. But my daily work, I mean, it's not something that I really actually apply to it too much. Maybe if I'm trying to create a novel texture on something, I could run a 2D CA on it, or a 1D CA, and like get some cool kind of things. Or if I want to, I do a lot of plotter art with my AxiDraw. So I do a lot of like 1D CAs where I, like extended neighborhood, like 5 neighbor 1D CAs, and then I plot it a lot. But for like my professional work, it doesn't really come into play too much unless I'm like trying to like embellish something with like a texture or something like that. That is like a cool one generated from a
He's in CD next, the next one, by the way.
Oh, he is?
Yeah.
Nice. Yeah, he's great. And he is really good at teaching too. So that's going to be nice. Oh, look, this is Jose Luis Garcia del Castillo. He's the guy who does GST 638.
Always with the green screen.
I know, he's got a nice setup there. I don't know how he's got that going on, but it's really good. So yeah, I mean, you can code the game of life, or you can code the general cellular automata, and then you can put anything plus the game of life, which is what we've done here.
So I guess that's it, huh?
Yeah, if anyone has any last question, now's the time, or forever hold your peace.
We'll call it, and then as usual, we'll get the video after for participants here through email. Look out for that, and just a reminder again about the webinar tomorrow if you're interested, and the next 2 weekends. And see you next. Check them out.
You guys post anything that you made from this course on Instagram, tag me. I'm at JAYMEZD, and follow me. And if you post it, I'll share it on the story or something for sure, because I'd love to see you guys' results. I haven't looked at my phone at all during this, so I don't know if someone has been posting anything. I'll definitely check it out afterwards. And I had a good time. I hope I can do another one of these soon, and maybe we'll tackle some even more complex.
V2.
V2
for sure.
Some more complex ones. I talked about could you modify this to always produce connected voxel regions? Well, and a subdividing automata? Well, maybe I've already figured those questions out, and the answer is yes, you can, and it's really cool. So there's some really interesting ones you can use, like Galapagos, to force it to create a connected structure. You search for like a rule that generates a connected structure, and that way you can, it's more suitable for like architectural ideas or 3D printing, because there's no floating little blocks like this. Let's see this little guy here. It's just floating in space. You don't want that. You want everything to be connected by the faces to each other. So there's some really interesting stuff. Thank you, Walter. So thanks, everybody. Yeah, I had a really good time. I hope you guys learned a lot.
Bye, everybody. Until next time. See you, James.
See ya. Bye, guys. Is that it?
Yeah, that's it.
Okay. All right.